Find a quiet place in the world where you can let the day slip away and let your mind wander through places shaped not by clocks and calendars, but by the deep rhythms of the earth itself. Tonight's journey takes us into the world of supervolcanoes, those huge hidden giants that sleep beneath our feet. They can reshape weather, continents, and even change the path of human history. Before we begin, I'd love to know where in the world you're listening from. Is it late at night in a city lit by street lamps, or early morning in the quiet before sunrise? Feel free to share in the comments. It's always amazing to see where our little community is listening from. And if you enjoy these calm explorations, a like and a subscribe would mean a great deal. To those already subscribed, thank you. You're part of the reason these quiet journeys can continue. I do hope this video helps you drift toward rest, and if by chance the story turns out to be a little too interesting and keeps you awake, well, at least you'll come away with a head full of strange landscapes and fiery mysteries. So let's settle in together. Close your eyes if you like. Breathe a little deeper and ask yourself this. If the ground beneath your feet held a force powerful enough to change the entire world, would you want to know? The Earth is often thought of as stable, a solid stage upon which history plays out. But beneath that quiet crust lies a restless world of melted rock, moving in slow currents like honey flowing through stone. Most of the time, these movements show themselves gently through the rise of mountains or the warmth of a hot spring, but sometimes pressure builds in silence until it is released in an eruption so huge that it makes any human measure of size look tiny. These are not the volcanoes you see standing against the horizon, cones of ash and fire. These are something different, something deeper, wider, and way more patient. The word supervolcano is in a way misleading. It suggests a volcano, but simply bigger. In truth, these are systems unto themselves, huge round holes in the ground that stretch for miles, underground rooms full of melted rock that can lie hidden for tens of thousands of years, and eruptions whose effects can echo across the entire planet. They are both creators and destroyers, putting minerals in soils even as they send ash into the skies, cooling the earth and darkening entire summers. In this journey, we will wander through their story, how they form, why they erupt, and what they leave behind. We'll visit Yellowstone, whose hot water shooting up and hot pools hint at the fires below. Toba, whose eruption may have touched the path of humanity. Taupo, Tambora, and others whose fury still lingers in history and legend. Along the way, we'll explore the science that allows us to look into the Earth's depths, the myths that humans have created to explain such fiery power, and the quiet truth of how rare and yet certain these giants really are. This will not be a tale of fear, but of perspective. For in the timeline of rocks and stones, the Earth is always reshaping itself, and in listening to its slow rumble, we can glimpse not only the dangers, but the wonders of a world that is very much alive. So let us begin with the ground beneath us and the fiery heart that makes our planet what it is. Beneath your feet right now, there is far more than soil, stone, and bedrock. The Earth may look like a solid ball that never moves, but in truth, it is a layered world built like an onion of unimaginable size, each layer carrying its own mysteries and movements. At the very center lies the core, a place of iron and nickel where temperatures reach well beyond the heat of the sun's surface. The inner part is solid, squeezed into hardness by huge pressure, while the outer core is melted, flowing slowly, churning like an endless ocean of liquid metal. It is this restless movement that creates the magnetic field around our planet, a shield that pushes away solar winds and allows life to grow. Above the core lies the mantle, the thickest part of our planet's body, stretching thousands of miles deep. The mantle is not melted in the way of a glowing pot. It is rock, yet rock that can creep and flow given enough heat and time. Imagine something between stone and taffy, shifting so slowly that continents are carried across oceans over tens of millions of years. This creeping motion is known as convection. As warmer material rises and cooler material sinks, setting up a planetary engine that never shuts down. It is here in the mantle that the slow heartbeat of Earth begins to show itself, pushing and pulling at the thin crust above. That crust, the layer we call home, is amazingly thin. On average, it is no thicker than the skin of an apple compared to the fruit beneath. There are two types of crust: continental, which carries mountains, rivers, and towns, and oceanic, which lies beneath the seas, thinner and heavier, constantly being created and destroyed at ridges and trenches. It is upon this fragile skin that every story of life has unfolded. Yet the real drama happens below, where heat builds, rock shifts, and pressure seeks escape. Melted rock, or magma, is not simply a fiery liquid waiting to burst forth. It is a mix of melted minerals, crystals, and gases dissolved under huge pressure. It seeps into cracks, pools into huge underground rooms, and sometimes creeps upward until it meets the surface. When it finally escapes, it becomes lava, spilling into the open air where it cools into new land. But volcanoes are not born from chance. They come from the movements of plates, the great slabs of crust that glide over the mantle's restless flow. Where plates pull apart, magma rises easily, filling the gap with fresh rock. This is how the mid-Atlantic ridge continuously creates new ocean floor. Where plates crash together, one is often forced downward into the mantle, carrying water and minerals with it. These additions lower the melting point of the surrounding rock, creating magma that climbs upward. This is why chains of volcanoes line the edges of the Pacific, forming the famous Ring of Fire. And sometimes volcanoes spring not from the edges of plates, but from hot spots where streams of heat rise directly from deep within the mantle. Hawaii is one such place, a chain of islands built by a wandering conveyor belt of lava. The rhythm of these processes is almost beyond human understanding. A volcano might sleep for thousands of years, gathering strength drop by drop in its underground room before letting out a sigh of ash and fire that lasts only days or weeks. It is as though the earth breathes in and breathes out, but on a time scale so long that our entire history is only a single shallow breath. To picture this heartbeat, think of a drum beat stretched so thin that each strike falls once every few thousand years. Slow, steady, but never stopping. Though we think of volcanoes as destroyers, they're also creators of continents, builders of islands, and recyclers of the planet's crust. Without them, there would be no towering Andes mountains, no rich soils of Java, no black sand beaches of Iceland. Even the air we breathe owes much to volcanic breathing over billions of years, which released water vapor and carbon dioxide into the skies of the early Earth. They are as much a part of life as the rain and the wind, though their patience and power can easily outlast us. And so the earth beneath our feet is never still. It is not a stage set in stone, but a restless body alive with currents, pressure, and fire. The crust may seem unmoving beneath your shoes, but in truth it is a raft upon seas of rock that flow like slow honey, carrying continents across the ages. Sometimes the raft shudders, sometimes it cracks, And sometimes it lets through a burst of melted energy that reminds us how alive the planet truly is. To walk upon the ground is to walk upon history in motion, shaped by forces that began long before us and will continue long after. The mountains, valleys, and plains we see are only temporary arrangements, rearranged endlessly by the deep, slow heartbeat of the Earth. The word supervolcano carries a kind of dramatic weight, as if it were the star of a disaster movie. But rock scientists did not invent the term to make headlines. It was born from the challenge of describing eruptions so huge, so beyond the ordinary, that no existing word seems good enough. A supervolcano is not simply a taller cone with a bit more lava on top. It is a rock event defined by size, a category saved for the rare eruptions that completely change the atmosphere, climate, and often the path of life itself. To pin down what makes an eruption super, scientists turn to the Volcanic Explosivity Index, or VEI for short. Think of it as a ruler for volcanic tantrums, ranking them not by height or width, but by how much material they hurl into the world. The VEI works in steps, which means each step up represents not a small nudge, but a 10 times increase in power. A level 1 eruption might be a gentle lava fountain in Hawaii, impressive but not devastating. A level 5 eruption like Mount St. Helens in 1980 blasted ash high into the sky and destroyed landscapes for miles around. The scale runs from 0 to 8, though 8 is more of a theoretical ceiling, a space saved for the very largest known eruptions in Earth's history. To reach this highest level, an eruption must throw out more than 1,000 cubic kilometers of material. That number is staggering enough on its own, but it helps to put it into perspective. Imagine the Grand Canyon, filled to the brim with volcanic ash, lightweight rock, and regular rock, not once but several times over. That is the kind of amount we're speaking of when we venture into the territory of supervolcanoes. By contrast, even some of the most notorious historic eruptions fall far below this mark. Mount Vesuvius, which buried Pompeii in the year 79, was a devastating event for the Roman world. Yet it was only a VEI level 5. Krakatoa in 1883, famous for creating a shock wave that circled the globe multiple times, barely reached level 6. Tambora in 1815 was larger still, VEI 7, so huge that it triggered the infamous year without a summer when crops failed across continents. Yet even Tambora, which caused worldwide hardship, did not break into the top level. Level 8 is saved for the true giants, the events so rare that none have happened in recorded history. When rock scientists speak of these colossal eruptions, they're talking about forces that unfold only once every several 100,000 years, perhaps even less often. They are not fireworks displays, but planetary-scale events. Ash clouds rise not just into the upper atmosphere, but beyond, spreading a veil that can dim the sun for years. Sulfur gases lift into the upper atmosphere, reflecting sunlight and sending global temperatures plunging. The result is what scientists call a volcanic winter, a spell of sudden cooling that can reshape ecosystems and stress the survival of species. The sheer size of such eruptions can be difficult to grasp, so let's imagine for a moment. A normal volcanic explosion might bury a nearby town. A supervolcano can blanket entire continents in ash. Crops would wither beneath darkened skies. Rivers would choke with volcanic debris. And even faraway regions untouched by lava or ashfall would feel the chill of a dimmed sun. While a normal eruption is a disaster for a region, a supervolcano is a disturbance for the entire globe. Another difference lies in the very shape of these giants. Many of the volcanoes we know, the classic cone rising above the horizon, are the result of smaller, repeated eruptions, building layer upon layer of rock. Supervolcanoes, on the other hand, are often invisible to the casual observer. They form huge depressions called calderas, created when an eruption empties. An underground room full of magma, and the surface collapses. What you might see today is a wide valley, a peaceful lake, or a rolling plateau with no looming mountain at all. Yellowstone's caldera, for instance, is so large that it is best appreciated from the air where its sprawling outline finally makes sense. Because they do not advertise themselves with sharp peaks or smoke plumes, supervolcanoes have a deceptive quietness. One might walk across a meadow, picnic beside a lake, or marvel at a hot spring, unaware that the ground beneath is the scar of an ancient eruption large enough to blanket half a continent in ash. Their hugeness is both awe-inspiring and unsettling. They hide in plain sight, patiently storing energy in underground rooms so huge they challenge the imagination. It is also worth noting that the very term supervolcano is more of a convenient shorthand than a precise scientific category. Nature does not recognize our labels. The Earth does not pause to check the VEI before deciding how much material to eject. The classification is a human attempt to make sense of events so extreme they strain our language. For most purposes, anything rated VEI 8 is considered a supervolcano, though eruptions just below that threshold can still be world-changing. To put the idea into another frame, think of volcanoes as voices in a choir. Some sing softly, releasing a trickle of lava that builds gentle islands. Others roar with power, filling the sky with ash and fire. But once in a great while, a voice emerges so thunderous it drowns out the rest, resonating not just across a single valley, but across the entire planet. That is the voice of a supervolcano, deep, rare, and unforgettable. And yet, for all their size, these eruptions are also a reminder of perspective. Our human sense of time is measured in decades, centuries at most. A supervolcano's timescale stretches into the tens of thousands of years. They may sleep for an age, their last outburst already ancient by the time the first towns rise. Their patience is huge, and when they stir, it is not in haste, but in slow certainty. Understanding what makes a supervolcano is not about sowing fear. It is about recognizing that our planet is alive in ways that defy human reckoning. To know that eruptions of such unimaginable magnitude are part of Earth's story is to be reminded of how vast and dynamic this world truly is. And if the thought feels overwhelming, there is comfort too. These events are exceedingly rare, separated by spans of time longer than the whole of recorded history. So when scientists speak of supervolcanoes, they're not conjuring scenes of panic, but painting a picture of the Earth as it is, restless, powerful, and patient. They're inviting us to see the ground beneath us, not as a fixed stage, but as part of a living system capable of whispers and of thunder. The whisper may be the warmth of a hot spring, the thunder the unimaginable eruption of a caldera. Both, however, are notes in the same long song, a song that stretches back billions of years and will continue long after we're gone. On the surface of the Earth, many landscapes appear calm, even ordinary. Meadows sway with wildflowers. Forests stretch across rolling hills, and lakes lie in peaceful stillness, their surfaces reflecting clouds and sky. Yet some of these landscapes are not what they seem. Beneath their quiet beauty lies a secret. They are the remains of explosion, so huge that the ground itself collapsed in exhaustion. These are calderas, huge scars left when a volcano erupts, not just upwards but also inward, creating depressions that can stretch for dozens of miles. A caldera forms in the wake of disaster. Imagine a giant underground room filled with melted rock, pressurized over thousands of years until finally the system gives way. The eruption is so huge that it empties much of the room in a matter of days or even hours. With the magma gone, there is nothing left to support the crust above. Like the roof of a cave collapsing after miners have taken away the supporting pillars, the surface caves in, leaving behind a wide, sunken basin. What remains is not the towering cone of a classic volcano, but a subtle depression, sometimes ringed with ridges, sometimes filled with water, sometimes covered over by new growth until it appears almost perfect. At first glance, a caldera doesn't advertise its dramatic beginnings. Unlike the sharp peaks of Mount Fuji or Mount Etna, a caldera might look like a pleasant valley or a shimmering lake. This deceptive quietness makes them both fascinating and a little eerie. You could drive across Yellowstone, stopping to marvel at geysers and hot springs, and never quite realize you're inside one of the largest volcanic scars on the planet. You might paddle across Lake Taupo in New Zealand, admiring the surrounding mountains without thinking that you're floating above the remains of one of Earth's most explosive eruptions. And if you were to stand at the edge of Lake Toba in Indonesia, gazing across waters so wide they seem like an inland sea, you would be standing on the rim of a caldera, born of an eruption that once dimmed the skies of the entire planet. Yellowstone is perhaps the most famous example. Stretching across Wyoming and into Montana and Idaho, it is a caldera so huge that its true outline is difficult to see from the ground. Instead, its story reveals itself in clues, the way the land rises and falls as if breathing, the constant hiss of hot water vents, the brilliant pools of hot water colored by tiny life. The park is celebrated for its beauty, but every geyser and bubbling spring is also a reminder that beneath lies a huge magma system, still very much alive. When rock scientists mapped the region, they discovered that Yellowstone had erupted several times in the past 2 million years, each event huge enough to alter global climate. Today it rests, though it continues to murmur through heat and steam. Across the Pacific in New Zealand lies Lake Taupo, another deceptively calm place. To stand on its shore is to see a jewel-blue expanse ringed by mountains that are often capped with snow. It looks like a setting for postcards and holiday cottages. Yet beneath those waters lies the largest volcanic lake on Earth. About 26,000 years ago, Taupo produced an eruption so violent that ash settled across both hemispheres. Even in China, nearly 7,000 miles away, ancient records speak of skies turned hazy. Later eruptions reshaped the lake again, and the most recent large event in the year 180 erupted with a force that would have been terrifying to witness, sending hot flows of gas and rock racing across the landscape at unimaginable speeds. Today, Taupo is a place of boating, fishing, and relaxation. Few who cast a line into its depths think about the inferno that carved it out. Then there is Lake Toba in Indonesia, the silent reminder of what may have been one of the most important eruptions in human prehistory. Around 74,000 years ago, the Toba eruption expelled an estimated 2,800 cubic kilometers of material, far surpassing any eruption in recorded history. The event left behind a caldera so large it is now filled by a lake more than 60 miles long. Scientists believe that the eruption caused a volcanic winter, plunging temperatures across the globe and potentially putting severe strain on early human populations. Some theories suggest a bottleneck in genetic diversity may have been linked to this eruption, though the debate continues. Whatever its precise impact, Toba was an eruption that reshaped both landscapes and lives. Today, Lake Toba is calm, a place where ferries cross the water and villages dot the shoreline. It is a setting of peace built upon the memory of chaos. What makes calderas so compelling is this contradiction. They are scars of violence, yet they wear disguises of peace. Their outlines soften over time, forests take root, rivers carve through, and life returns, often more fertile than before. Yet beneath that surface, the volcanic systems may still be active, biding their time. In some cases, small eruptions build new cones within the larger basin, like miniature volcanoes growing in the shadow of their collapsed ancestors. At other times, the caldera remains dormant, leaving behind only the deceptive quiet of lakes and plains. And here lies the humor of it. If you ever stumble across a lake that seems a little too circular, a little too neatly drawn as though sketched with a compass, it might not be just a lake. It might be the mouth of a supervolcano long since filled with water, disguising itself as a perfect circle of calm. Nature, after all, rarely draws straight lines, so a suspiciously geometric body of water deserves a raised eyebrow. But these features are not rare oddities. Calderas are found across the world, from North America to Asia, from the Mediterranean to South America. Some are huge and infamous, like Yellowstone or Toba. Others are smaller but still remarkable, like the caldera of Santorini in Greece, which gave rise to legends of a sunken civilization. Each tells the same essential story. When Earth releases its power in extraordinary fashion, the land can collapse under the weight of its own absence. To walk across such a place is to tread upon a paradox. The meadow may be quiet, the lake may be mirror smooth, the hills may seem gentle, yet every tree, every ripple, every blade of grass owes its existence to an ancient fury. Calderas remind us that peace and violence are often intertwined in nature. What seems timeless and calm may in fact be a wound slowly healing, a scar hidden beneath a cover of water and soil. So when rock scientists speak of calderas, they are not just describing holes in the ground. They are describing the Earth's ability to reshape itself, to collapse and renew, to hide huge dramas beneath ordinary scenery. A caldera is a place where the Earth has sighed so deeply that the crust itself has sunk inward, leaving behind a hollow that time and life slowly soften. It is at once a reminder of destruction and a stage for rebirth, proof that the world beneath us is always alive, always waiting, and always more mysterious than it seems. In the heart of North America, tucked within the rolling mountains and sweeping forests of Wyoming, Montana, and Idaho, lies Yellowstone National Park. To most who visit, it is a wonderland of geysers, hot springs, and wildlife, a place where bison wander across steaming fields and rainbow-colored pools shimmer like jewels. Yet, beneath the postcard views is something far larger and far older, one of the most remarkable volcanic systems on Earth, a supervolcano that has shaped the continent again and again. The history of Yellowstone's eruptions stretches back more than 2 million years. The first known giant event happened about 2,100,000 years ago, creating the Huckleberry Ridge Tuff, a layer of volcanic rock spread across huge distances. That eruption carved out a caldera so huge it makes mountain valleys look like tiny scratches. By comparison, roughly 1,300,000 years ago, another massive eruption reshaped the land again, forming the Henry's Fork caldera. Then about 640,000 years ago, the most recent super-eruption occurred, expelling over 1,000 cubic kilometers of material, and leaving behind the giant depression that dominates the park today. Each of these events would have been devastating for life across the Northern Hemisphere. Yet they are spaced across hundreds of thousands of years, intervals so long they stretch the imagination. What we see at Yellowstone now is the afterglow of those ancient outbursts. The underground room beneath still simmers, sending heat upward through cracks in the crust. That heat drives one of the most extraordinary hot water systems on the planet. Old Faithful, perhaps the most famous geyser in the world, erupts with punctual bursts of steam and water, delighting visitors who gather in hushed anticipation. Nearby, the grand prismatic spring blazes with colors so bright they seem painted, turquoise, emerald, orange, caused by heat-loving tiny organisms that thrive in the mineral-rich waters. Mud pots bubble like cauldrons, fumaroles hiss with vapor, and entire valleys are strung with steaming pools that seem to breathe with the planet itself. This hot water activity is not merely a spectacle. It is a signal, a constant reminder that the forces beneath Yellowstone remain alive. Yet it would be a mistake to think of the park as a ticking bomb just waiting to explode. Popular culture has often stoked that fear. Documentaries and films warn of an overdue eruption, suggesting that Yellowstone follows some strict schedule like a punctual commuter train. The reality is far more complex. Geology does not keep to timetables, and the notion of Yellowstone being overdue is a myth that scientists have repeatedly worked to dispel. The truth is that eruptions, especially of the supervolcanic kind, do not follow regular intervals. The past 3 Yellowstone events occurred at very different times, separated by about 800,000 years between the first and second, and then roughly 660,000 years between the second and third. Those numbers are averages, and averages are misleading when applied to something as chaotic and rare as volcanism. To suggest that the volcano is due simply because a certain span of time has passed is to misunderstand how these systems function. In fact, the overwhelming majority of Yellowstone's activity over the past few 100,000 years has not been explosive at all. Instead, it has produced smaller lava flows, the last of which occurred about 70,000 years ago. These were not global catastrophes, but local reshaping events, creating ridges and flows within the caldera. The volcano's more common language is not the deafening roar of a super eruption, but the slow, steady breathing out of heat expressed through geysers, hot springs, and occasional flows of melted rock. To understand Yellowstone's true nature, scientists monitor it constantly. Networks of earthquake detectors pick up even the faintest tremors, while satellites measure how the ground rises and falls over time. These surveys reveal that Yellowstone breathes, swelling and dropping by inches as magma shifts below. Sometimes the ground lifts, sometimes it sinks. These motions are natural and do not necessarily point to an approaching disaster. In fact, they are signs of a living system adjusting itself, like the gentle rise and fall of a sleeper's chest. Of course, the idea of a Yellowstone eruption has captured imaginations because of its scale. If it were to erupt with the same magnitude as in the distant past, the effects would indeed be felt worldwide. Ash could blanket much of North America. Crops might fail, and the global climate would cool for years. Yet scientists emphasize that the likelihood of such an event in any human lifetime is extremely small. The odds are so low that humanity faces far greater risks from earthquakes, smaller volcanic eruptions, or even everyday weather events than from Yellowstone suddenly unleashing its fury. Still, myths persist. Some imagine Yellowstone as a powder keg on the brink, its eruption imminent. Others see it as part of apocalyptic prophecies, blending science with speculation. But when we strip away the drama, what remains is something both more reassuring and more fascinating. Yellowstone is not a doomsday clock, but a natural laboratory offering insights into the inner workings of our planet. By studying it, scientists gain knowledge not just about one volcano, but about the processes that shape continents, oceans, and atmospheres across the globe. And so Yellowstone is best understood not as a threat hanging over us, but as a reminder of Earth's huge power and patience. Its geysers and hot springs are whispers from the deep, not warning bells, but voices of a system that has existed for millions of years and will continue long after our lifetimes. It is a sleeping giant, yes, but a giant with a rhythm so slow that human history is a flicker in its dream. To walk across its meadows, to feel the heat of its vents on a cold morning, is to stand atop a living scar, one that tells of violence long past and vitality still present. When visitors marvel at Old Faithful or photograph the radiant colors of the grand prismatic spring, they're not just enjoying tourist spectacles. They are, knowingly or not, witnessing evidence of Earth's restless heart. Yellowstone is a giant, but one whose story is not written in looming doom, but in the quiet and constant reminder that the ground beneath us is alive and that patience on the scale of thousands of years is the natural language of the planet we call home. About 74,000 years ago, in the lush and volcanic landscapes of what is now Indonesia, the Earth released a breath so huge that it echoed across the entire planet. This was the eruption of Toba, one of the largest volcanic events known in human history. To stand at Lake Toba today is to see placid waters stretching over 60 miles, ringed by green hills and dotted with villages. It feels peaceful, even timeless. Yet this enormous lake is in fact the scar of a super eruption, so powerful that it may have brushed against the very survival of our species. The size of the Toba eruption defies easy imagination. In a matter of days, perhaps even hours, more than 2,800 cubic kilometers of material were expelled. Ash, lightweight rock, and volcanic gases blasted into the sky with a force that no human being has ever witnessed firsthand. That volume is more than 40 times larger than the eruption of Tambora in the year 1815, which itself produced a year without a summer. The eruption cloud would have risen far above the upper atmosphere, spreading out across the globe. Ash rained down across South Asia, India, and as far as the Middle East. Deposits from this eruption have been found thousands of miles from the source, a fine gray reminder of the fury that once poured from the Earth's depths. The immediate consequences for the surrounding region would have been devastating. Entire landscapes would have been buried in meters of ash, rivers clogged, forests destroyed, and life suffocated beneath layers of debris. Yet the more profound effects of Toba were not confined to Indonesia. The gases and ash launched into the atmosphere formed a veil that reflected sunlight back into space. Temperatures around the world are thought to have dropped significantly, ushering in what is known as a volcanic winter. For years, scientists debated just how severe this cooling might have been. Some estimates suggested a global temperature drop of several degrees, enough to stress ecosystems everywhere. Others argue the effects may have been shorter and less dramatic, with impacts varying across regions. What is clear is that the eruption altered climate patterns, disrupted rainfall, and likely caused widespread ecological stress. For early humans, who lived in small, scattered groups dependent on hunting and gathering, even a modest shift in climate would have posed a serious challenge. This is where the story of Toba enters the realm of human origins. Some researchers have proposed that the eruption triggered a genetic bottleneck in our species. The idea is that the sudden cooling and ecological collapse reduced human populations to as few as several thousand individuals, perhaps even fewer, forcing them into isolated refuges where survival was barely possible. Genetic evidence does show that humanity went through a period of reduced diversity tens of thousands of years ago. For some, Toba has been suggested as the culprit. Yet this theory is not without controversy. While it is tempting to link the eruption directly to the genetic bottleneck, newer evidence complicates the picture. Archaeological sites in Africa and India show continuity of human presence before and after the eruption, suggesting that while conditions may have been harsh, humans were not wiped out entirely. It is possible that populations dwindled in certain regions while persisting in others, or that the genetic bottleneck had other causes, such as long-term migrations and environmental pressures unrelated to Toba. In short, the story remains debated, a reminder that the Earth's history and humanity's story are woven together in ways that are complex and still being unraveled. Regardless of the details, what is beyond doubt is that early humans lived through this extraordinary event. Imagine a world where the sky darkened for months, where the air grew colder, where familiar plants withered and animals struggled to find food. Communities would have been forced to adapt quickly, seeking new food sources, traveling to more hospitable regions, or relying on ingenuity and cooperation to endure. The fact that humans persisted through this upheaval speaks to resilience, creativity, and sheer chance. Had circumstances been only slightly different, our story might have ended there, lost in a haze of ash and cooling skies. Toba, then, is not merely a geological tale, but also a human one. It reminds us how finely balanced survival can be, how a single eruption can tilt the scales of life across the globe. For the ancestors of modern humanity, it was a trial not of days or weeks, but of generations. Children would have grown up in a dimmer, colder world, learning new ways to survive. Elders would have shared knowledge of shifting landscapes, guiding families toward scarce resources. Entire groups may have vanished, leaving no trace except in the strands of DNA that all of us carry today. Lake Toba itself is a testament to both destruction and renewal. Over tens of thousands of years, the collapsed caldera filled with water, creating the largest volcanic lake on Earth. Its blue waters now shimmer under the sun, and the island of Samosir rises from its center, formed by rising domes as magma continued to shift beneath. What was once a scar of unimaginable force has become a place of beauty, a home to communities and cultures that live unaware of, or perhaps unfazed by, its fiery past. There is something quietly humbling in this contrast. The same lake that draws travelers for its beauty was born in one of the darkest episodes in human prehistory. The same eruption that may have reduced our species to its slimmest margins has, with time, become a cradle of life once more. The Earth erases and renews, and in doing so, it reminds us that survival is always provisional, always balanced on the edge of change. Whether or not Toba nearly extinguished humanity, it certainly shows how fragile life can be in the face of planetary forces. We live at the mercy of events far beyond our control. Yet within that vulnerability lies a story of persistence. Our ancestors endured the dim skies, the failing crops, the scarcity of food, and somehow passed through the shadow into light again. Every person alive today is proof of that endurance. So when we look across the calm waters of Lake Toba, it is worth pausing to imagine the silence that followed the eruption, the ash settling on forests, the sudden chill, the long winters. Then it is worth remembering the people who walked through that silence, who endured, and who handed forward the gift of survival. In that sense, Toba is not only a story of destruction, but a quiet celebration of the improbable resilience of humanity, surviving against odds that might easily have tipped the other way. In the center of New Zealand's North Island lies a body of water so huge that it could easily be mistaken for an inland sea. Its surface glitters in the sunlight, framed by distant mountains that are often capped with snow, and along its shores, towns bustle quietly with life. This is Lake Taupo, the largest freshwater lake in Australasia, a place of beauty, recreation, and cultural significance. To gaze upon it today is to see calm, but beneath that calm surface lies a history of ferocity. Taupo is not just a lake, it is a caldera, the remnant of eruptions so powerful that they reshaped landscapes and left echoes around the globe. Taupo's story is one of recurring fire. Around 26,000 years ago, an eruption of staggering scale created the modern caldera. Known as the Orowanui eruption, it was the most recent super-eruption on Earth, ejecting more than 1,000 cubic kilometers of material. Ash from Orowanui has been found across the Pacific, even as far as Antarctica, a reminder of how interconnected the planet becomes during such an event. The eruption destroyed forests, dammed rivers, and carved out the depression that would eventually fill with water to become Lake Taupo. To imagine it is to imagine skies blackened with ash, rivers boiling with volcanic debris, and an entire island nation cloaked in darkness. But Taupo's fury did not end there. About 1,800 years ago, the caldera roared again in what is often called the Hatapi eruption. Though smaller than Orowanui, it was still among the most violent eruptions in the last 2,000 years, releasing enough force to devastate central New Zealand. Hot flows of gas and rock surged across the land at tremendous speed, flattening forests and leaving behind barren landscapes of lightweight rock and ash. The eruption was so explosive that ancient Chinese records thousands of miles away described unusual skies, likely caused by the drifting volcanic haze. For the Maori people, who would later settle in Aotearoa, the land around Taupo held a memory of fire that found its way into oral tradition. Maori culture is deeply tied to the landscapes of New Zealand, and volcanic features often carry stories that blend myth, family history, and place. Lake Taupo is no exception. According to tradition, the lake was created by the actions of Ngatoroi-Rangi, a great tohunga or priest who brought fire from his ancestral homeland to warm the land of Aotearoa. Other legends speak of battles between powerful ancestors, their struggles shaking the earth and shaping the mountains. For many Maori, the volcanic heart of the North Island is not a lifeless geological feature, but a living presence, a place imbued with whakapapa, or spirit. The land remembers, and through story, so do the people. These legends, while poetic, also reflect an understanding that the land is alive and powerful. Volcanoes are not viewed merely as threats, but as ancestors and forces woven into the fabric of identity. Mountains like Tongariro, Ngauruhoe, and Ruapehu, which stand near Taupo, are personified in traditions, their relationships and rivalries shaping the landscape itself. To live in this volcanic heartland is to accept both the gifts and the risks of a land that can be fertile and destructive in equal measure. The myths preserve not just awe, but wisdom. Respect for the land, for it holds the power to both nourish and overwhelm. What is striking about Taupo is how its violence has given rise to beauty and abundance. The eruption that carved its basin also enriched the soils, creating landscapes where forests could regrow and life could flourish. Today, the lake is a center for recreation, its clear waters drawing anglers, sailors, and swimmers. The surrounding region, with its hot water fields and mountain peaks, has become one of New Zealand's most iconic destinations, celebrated both by locals and visitors from afar. It is a reminder that what was once destruction becomes, with time, the foundation for new life and new stories. The relationship between people and Taupo reflects a broader truth. Landscapes shape culture just as much as culture interprets landscapes. The Maori view of volcanic regions as living entities contrasts with the scientific lens of geology. Yet both speak to the same reality, that Taupo is not inert. Its past is fiery, its present is alive with hot water whispers, and its future is uncertain. Scientists continue to monitor earthquake tremors, ground movement, and lake chemistry, watching for signs of unrest. But for the communities that live by its shores, Taupo is also a source of livelihood and identity, its waters woven into daily life. To understand Taupo is to hold both scales in mind. The geological, where eruptions are measured in tens of thousands of years, and the human, where generations live and die within the shadow of a caldera. For the geologist, Taupo is a natural wonder, a place that offers insight into the workings of supervolcanoes. For the Maori storyteller, it is an ancestor, a being with spirit and history. For the everyday resident, it is home, a place of fishing trips, family gatherings, and evening reflections as the sun sets behind the hills. It is also worth noting how Taupo's story connects with the wider world. The Tepe eruption of around 1,800 years ago is sometimes considered the most violent eruption in the last 5,000 years. That means it outstripped even Krakatoa in 1883, which shattered islands and sent tsunamis across oceans. Yet while Krakatoa was witnessed by modern societies and recorded in newspapers, Tepe occurred before written history in New Zealand. Its memory survives in the land itself and perhaps in the sky-watching records of distant civilizations who noticed strange atmospheric effects without knowing their source. In that sense, Taupo represents the hidden threads that connect Earth's regions. A burst of fire in New Zealand can alter the skies of China, while a plume of ash from Indonesia can cool climates in Africa. These connections remind us that volcanoes are not merely local events. They are planetary ones, and Taupo, with its eruptions, large and small, has played its part in shaping both the land of Aotearoa and the broader Earth. To stand at the shore of Lake Taupo today is to stand on the edge of a paradox. The water is calm, the air is fresh, the horizon is peaceful. Yet that calm rests atop the memory of violence and the possibility, however distant, that it may one day return. For now, it is a place of beauty, a jewel in the heart of New Zealand. Its story is one of fire and water, of myth and science, of destruction and rebirth. Taupo is not just a lake, nor just a caldera. It is a reminder that the Earth's power is both terrifying and magnificent, and that human culture is always, in some way, shaped by the land beneath our feet. In the spring of 1815, on the Indonesian island of Sumbawa, the Earth let out a roar so mighty that it remains the largest volcanic eruption recorded in human history. This was Mount Tambora's catastrophe, an event that reshaped not only the landscape of Indonesia, but the very climate of the globe. To the people who lived nearby, it must have seemed as though the world itself had cracked open. To the wider world, which would soon feel its icy breath, it became known as the cause of the year without a summer. Mount Tambora had stood tall, a proud volcanic peak rising over 4,000 meters, one of the highest in the Indonesian archipelago. But in April of that year, its crown was shattered. A series of eruptions shook the mountain, culminating on April 10th and 11th, in an explosion so huge it could be heard more than 1,000 miles away. In fact, the sound carried as far as Sumatra, and some accounts reported it was mistaken for cannon fire. The eruption column soared into the upper atmosphere, ejecting an estimated 160 cubic kilometers of material. Ash, lightweight rock, and gases hurled skyward in a matter of hours. The immediate devastation was beyond comprehension. Hot flows of gas and rock cascaded down the mountain's flanks, incinerating villages and obliterating everything in their path. Entire communities were erased. The explosion reduced Tambora's height by more than 1,000 meters, collapsing its summit into a gaping caldera 7 kilometers wide. Tens of thousands of people living on Sumbawa and nearby islands perished from the eruption itself or from the famine and disease that followed. But Tambora's impact did not end at the shores of Indonesia. Its true legacy would be carried on winds around the globe. Sulfur dioxide from the eruption spread high into the upper atmosphere, where it transformed into tiny particles that reflected sunlight back into space. This thin veil of volcanic haze dimmed the earth, reducing temperatures worldwide. Crops failed in Europe, Asia, and North America, not from lava or ashfall, but from cold and darkness. The year 1816 became infamous as the year without a summer, a season where frost struck in June and snow fell in July. In New England, farmers watched helplessly as fields of corn blackened under sudden freezes. Across the Atlantic in Europe, relentless rain and unseasonable chill ruined harvests, leading to food shortages and rising grain prices. The consequences were felt far beyond the farms. Starvation and malnutrition spread in regions unaccustomed to such scarcity. In Ireland, already fragile from economic hardship, famine took a brutal toll. In China, disrupted monsoons caused flooding in some areas and drought in others, compounding human suffering. Famines led to migrations as desperate families left their homelands in search of more stable climates. In Germany, where hunger was widespread, discontent helped spark political unrest. All of this was triggered not by war or economics, but by a mountain's eruption thousands of miles away. Amid this bleakness, Tambora left another kind of mark, one upon art and imagination. In the summer of 1816, a group of writers found themselves on the shores of Lake Geneva, trapped indoors by the dreary weather. Among them was a young woman named Mary Shelley. With the rain lashing against the windows and the sky perpetually gray, she took part in a storytelling challenge. From that exercise emerged Frankenstein, a novel that fused science, horror, and the question of what it means to create life. The monster's brooding presence, shrouded in storms and gloom, can be traced back to the shadow of Tambora, its ash still dimming the skies of Europe as she wrote. Her companion that summer, Lord Byron, was equally influenced by the dismal weather. He composed the poem Darkness, a haunting vision of a sunless world where the bright sun was extinguished. Though he was not describing the eruption itself, the imagery echoed the strange twilight that Europe endured in those months. It is a reminder that natural events can ripple into culture, shaping the stories and art we carry forward. Tambora's eruption did not merely cool the earth. It stirred the imagination. Science, too, found lessons in the catastrophe. Though volcanology was not yet a formal field, scholars noted the link between the eruption and the global climate anomalies. It was one of the first events to demonstrate in clear terms that volcanoes could influence weather and agriculture on a planetary scale. The notion that a mountain's outburst in Indonesia could cause frosts in North America helped pave the way for modern understandings of atmospheric circulation and climate systems. If the eruption was a story of destruction, it was also one of resilience. Communities devastated by famine rebuilt, though scars remained. New migrations reshaped demographics. Some families who fled Europe during the food shortages found new beginnings in North America. In this way, Tambora's eruption indirectly altered the patterns of settlement and history, leaving fingerprints not just on landscapes but on societies. Today, the caldera of Tambora still yawns at the summit of the mountain, a silent reminder of the explosion that once shook the world. The volcano is not extinct, but it slumbers, its slopes now green with forest. Villages have returned to its base, and life goes on much as it did before the eruption. For locals, Tambora is a presence in the background, not a constant threat. Yet for historians and rock scientists, it remains a case study in how Earth's power can ripple outward into every corner of human life. There is a sobering irony in Tambora's story. The eruption devastated lives and caused untold suffering. Yet it also gave rise to cultural treasures, scientific insights, and even migrations that reshaped nations. It is a reminder that catastrophe and creation often travel hand in hand. The Earth's violence can strip away, but in the aftermath, humans find ways to rebuild, to adapt, and to create meaning from the shadows. To think of Tambora is to think of a mountain that roared so loudly its echoes were heard across centuries. It is to remember the hungry families staring at withered fields, the poets gazing out at stormy skies, the scientists piecing together the link between eruption and climate. And it is to recognize that all of these stories, the suffering, the creativity, the resilience, are intertwined, threads spun from the same fiery core. Tambora's eruption stands as the greatest volcanic event of recorded history. It humbled empires, darkened skies, and chilled summers. But it also seeded art and knowledge, leaving us not only with cautionary lessons, but with creations that endure. When one looks at the world today, it is remarkable to think that a single volcano on a remote island nearly 2 centuries ago could ripple into so many facets of human existence. That is the power of Earth's fire. Destructive, yes, but also transformative, shaping not just landscapes, but the very course of human history. Deep beneath the Earth's surface, hidden from view but central to the story of volcanoes, lies magma, the melted rock that fuels eruptions, builds new land, and occasionally reshapes the planet in dramatic fashion. At first glance, magma might seem like a simple concept. Liquid rock heated until it flows. But as with many of Earth's processes, the truth is far more intricate. Not all magma is the same, and the differences between varieties explain why some volcanoes ooze gently like honey, while others explode with devastating violence. Understanding magma is like understanding the temperament of the Earth itself. For in its chemistry lies the secret of why volcanoes behave the way they do. The most basic way to classify magma is by its composition, particularly the amount of silica it contains. Silica, a compound of silicon and oxygen, is a major ingredient in most rocks. The higher the silica content, the more viscous or sticky the magma becomes. Think of it like sauces in cooking. A thin broth flows easily while a thick stew resists movement. The same principle applies to melted rock. At the runniest end of the spectrum is basaltic magma. It has relatively low silica content, around 45 to 55%, which makes it fluid and quick to flow. Basaltic eruptions are typically less explosive because gases escape easily from the thin liquid. This is the kind of magma that creates the broad, shield-shaped volcanoes of Hawaii, where lava fountains and rivers of melted rock can stream for miles without much interruption. These eruptions can be spectacular and destructive to property, but they are not usually the sort of events that darken skies or collapse continents. On the opposite end is rhyolitic magma, which contains more than 70% silica. This high concentration gives rhyolite a thick, pasty quality, more like tar than water. The problem with such stickiness is that gases trapped inside find it difficult to escape. Pressure builds as bubbles struggle against the heavy magma, much like steam in a tightly sealed pot. When the system finally fails, the result is a sudden, violent release, an explosive eruption that sends ash, lightweight rock, and hot flows of gas and rock hurtling outward. Many of the most catastrophic eruptions in history, including those linked with supervolcanoes, are powered by rhyolitic magma. Between these two extremes lies andesitic magma, named after the Andes Mountains where it is common. Its silica content sits in the middle range, around 55 to 65%, and so does its behavior. Andesitic eruptions can be more explosive than basaltic, but generally less extreme than rhyolitic. Mount St. Helens in 1980, for instance, was driven by andesitic magma, producing a powerful blast, but not on the scale of a supervolcano. Viscosity, then, is the key to understanding how magma dictates volcanic personality. A volcano fed by runny basalt tends to flow calmly, albeit destructively, across the land. A volcano supplied with sticky rhyolite builds up pressure until it erupts like a shaken bottle of soda, suddenly uncapped. The difference is not subtle. It is the reason one eruption creates gentle lava fields while another devastates entire regions. Supervolcanoes fall squarely into the rhyolitic category. Their underground rooms, huge reservoirs buried beneath the crust, are filled with this thick, silica-rich material. Over thousands of years, these rooms slowly accumulate more and more melt, absorbing heat and gases from the mantle below. Because rhyolitic magma resists the escape of gas, it becomes like a giant pressure cooker. The larger the room grows, the more potential energy it stores. Eventually, the system can reach a tipping point where the sheer volume of pressurized magma causes the crust above to fail catastrophically. When it does, the eruption is not a cone-top blast, but the collapse of an entire region, spewing unimaginable amounts of ash and lightweight rock into the sky. The gases dissolved in magma are equally important to its behavior. Water vapor, carbon dioxide, and sulfur dioxide are the most common, and their presence makes all the difference. In basaltic magma, gases escape with relative ease, forming fountains of lava that spurt upward in dazzling displays. In rhyolitic magma, however, the gases are locked in until the pressure becomes unbearable. When they finally break free, the rapid expansion tears the magma apart, fragmenting it into ash and lightweight rock that are blasted outward with terrifying force. This is why supervolcanoes don't just flow, they explode. The chemistry of magma also influences what happens after an eruption. Basaltic lava cools into dark, dense rock, building new ocean crust and forming islands. Rhyolitic eruptions, by contrast, scatter light, frothy, lightweight rock and ash across vast distances. These fine particles can remain suspended in the atmosphere for months or years, reflecting sunlight and cooling the planet. Thus, the stickiness of the magma beneath our feet can ultimately affect the climate above our heads. It might seem odd that such a fundamental part of geology comes down to something as subtle as how gooey the magma is, but viscosity is destiny. To borrow an everyday metaphor, It's the difference between spilling a glass of water and dropping a jar of honey. Water spreads quickly and without much fuss. Honey resists until suddenly it gives way, splattering thickly in all directions. Add in gas bubbles, and the difference is even more striking. Carbonated water fizzes gently, while thick carbonated syrup would burst explosively. That is, in essence, the difference between basaltic flows and rhyolitic supereruptions. One of the more fascinating aspects of magma science is how temperature and chemistry work together. Basaltic magma is hotter, often over 1,000 degrees Celsius, which further reduces its viscosity. Rhyolitic magma is cooler, around 700 to 800 degrees Celsius, making it stiffer still. Even small changes in temperature can alter the magma's ability to flow, which in turn affects how easily gases escape. These details, measured in laboratories and observed in field studies, provide the key to predicting how a volcano might behave. Of course, the Earth rarely plays by simple rules. Underground rooms can evolve over time, mixing different types of melt. Basaltic magma rising from the mantle may intrude into a rhyolitic chamber, adding heat and stirring the system like a spoon in porridge. This can suddenly change the dynamics, increasing pressure and setting the stage for an eruption. Volcanologists study these processes with great care, analyzing crystals, gases, and rock chemistry to reconstruct the stories hidden in each eruption. Supervolcanoes are particularly challenging to study because they do not erupt often. Their rhyolitic chambers grow silently over tens of thousands of years, their surfaces covered by forests, lakes, or even towns. The signs of unrest may be subtle: slight swelling of the ground, tiny earthquakes, changes in the composition of gas emissions. Beneath that calm, however, lies a reservoir of sticky magma waiting for the right conditions to release its energy. To think about magma is to appreciate the complexity beneath the crust. It is not a uniform sea of melted rock, but a diverse, ever-changing mixture. Its properties dictating the shape of continents and the fate of civilizations. The difference between a gentle lava flow and a planet-altering explosion comes down to silica content, temperature, gas, and time. Each eruption is a performance directed by the chemistry of the melt. There is something oddly poetic in this. The very stickiness of rock, a property so mundane it could be compared to kitchen condiments, determines whether a volcano builds new islands or blankets continents in ash. Supervolcanoes owe their terrifying might not to being hotter or larger alone, but to being filled with rhyolitic magma, the slowest, thickest, most reluctant of Earth's melted materials. It is this reluctance to flow that makes their eventual release so spectacular and so rare. So, the science of magma is more than just chemistry. It is the story of Earth's temperament. Basalt flows with ease, spreading calmly across the land. Andesite balances between fluidity and pressure, sometimes quiet, sometimes fierce. Rhyolite clings stubbornly to its gases until it can hold no more, then erupts with world-changing violence. In these hidden differences lies the explanation for why the planet sometimes whispers in steam and lava, and at other times shouts in explosions that can alter the course of life itself. When a volcano erupts, the first images that often come to mind are rivers of lava, collapsing mountainsides, or clouds of ash rolling down into valleys. These are dramatic, immediate, and devastating for those nearby. Yet some of the most powerful effects of volcanism happen not in the moments after an explosion, but in the months and years that follow, carried aloft into the skies. High above the earth, invisible to most eyes, ash and sulfur, tiny particles can weave a veil around the planet, filtering sunlight, cooling temperatures, and sometimes throwing entire societies into crisis. This is the story of volcanic winters, when eruptions rewrite the climate and remind humanity of how dependent we are on the warmth of the sun. To understand how such cooling happens, imagine the sky not as empty blue, but as a layered system of currents and chemistry. When a volcano erupts with great force, it does more than scatter dust across the ground. It can blast fine particles of ash and droplets of sulfur dioxide all the way into the stratosphere, the atmospheric layer above the weather we experience daily. Unlike lower-level emissions that are quickly washed out by rain, material in the stratosphere can linger for months or even years, spreading around the globe. Sulfur dioxide reacts with water to form tiny droplets of sulfuric acid, each one acting like a microscopic mirror, reflecting a fraction of sunlight back into space. The more extensive the veil, the less energy reaches the Earth's surface and the cooler the world becomes. Even small reductions in solar radiation can have outsized effects. A drop in global temperature by just 1 or 2 degrees Celsius might not sound catastrophic on paper, but for ecosystems and agriculture, it can mean the difference between abundance and famine. Crops tuned to precise growing seasons can fail, rainfall patterns can shift, and glaciers can grow. In the past, volcanic winters have been linked to failed harvests, migrations, and even social unrest. One of the clearest examples comes from the eruption of Mount Tambora in 1815. As sulfur particles spread across the atmosphere, temperatures dipped across much of the northern hemisphere. The following year, 1816, became infamous as the year without a summer. In New England, farmers woke to frost in June. Their cornfields blackened, as though winter had returned. Snow fell in July, a cruel parody of the season. Across Europe, rains fell relentlessly while the air remained chill, turning fields into mud and ruining harvests. Bread prices soared, hunger spread, and people migrated in search of better conditions. This was not a local problem. It was a global shockwave from a single eruption. Another notable case occurred in the year 1257, when the eruption of Samalas in Indonesia lofted immense quantities of material into the sky. For centuries, the source of this event was a mystery, inferred only from ice core records that showed sudden spikes in sulfur. Today, evidence from Lombok Island confirms that Samalas was responsible. The climatic impact was severe, contributing to years of cooling that affected societies across the medieval world. Chronicles from Europe and Asia mention unusual weather, failed crops, and famine, a thread woven into human history by a distant eruption. Even eruptions smaller than Tambora or Samalas can produce noticeable cooling. The eruption of Krakatoa in 1883, though less powerful, still dimmed sunsets around the world. Painters in Europe marveled at the lurid, blood-red skies, capturing them in art that still hangs in galleries today. Observers as far away as New York reported unusual twilight colors. Meanwhile, global temperatures dropped slightly, reminding everyone that volcanoes need not be supersized to leave a worldwide mark. The Toba eruption, some 74,000 years ago, remains the most extreme example. Though scientists debate the exact climatic consequences, many believe it triggered a pronounced volcanic winter, with cooling severe enough to threaten human populations. Even if the bottleneck theory, that humanity was reduced to only a few thousand individuals, is questioned today, there is little doubt that Toba altered climates dramatically for years, if not decades. For our ancestors, survival meant adapting quickly to an environment that had grown suddenly harsher. These examples highlight a crucial point. Volcanoes and climate are inseparably linked. Eruptions may be brief, but their atmospheric effects ripple across seasons and continents. They are, in a sense, experiments in planetary engineering carried out by nature itself. With one colossal outburst, the Earth demonstrates how fragile our balance of sunlight and temperature truly is. This naturally invites comparison with modern discussions of climate change. Today, the warming of the atmosphere is driven not by volcanoes, but by human activity, particularly the release of carbon dioxide and other greenhouse gases. Unlike volcanic cooling, which tends to be sharp but short-lived, human-induced warming is gradual but persistent, building over decades and centuries. Yet the principle that altering the atmosphere alters the climate is the same. Both show how the thin envelope of gases around our planet controls conditions for life. Interestingly, some scientists have even studied volcanic winters as a guide for geoengineering. The idea is that if sulfur particles can reflect sunlight and cool the planet after an eruption, perhaps humanity could mimic the process deliberately to counteract global warming. The concept is highly controversial, for while it could potentially lower temperatures, it also risks disrupting rainfall, damaging ozone, and creating new unforeseen problems. Tambora's legacy, then, is not just a historical cautionary tale, but a real-world example used in debates about our future. Volcanic winters also remind us that climate is not static. It is sensitive, reactive, and easily perturbed. A single eruption can change weather patterns for years, while repeated events over centuries can alter entire epochs. Some scientists suggest that a cluster of eruptions may have contributed to the onset of the Little Ice Age, a period of cooler temperatures from the 14th to the 19th centuries. If so, then the daily struggles of medieval farmers, the freezing of rivers like the Thames, and even shifts in political power were influenced in part by the pulse of fire beneath the earth. The human experience of these winters has always been marked by contrast. On one hand, there is hardship. Crops fail, hunger spreads, and societies strain under the pressure of scarcity. On the other, there is awe. Sunsets glow with unearthly colors, skies shimmer with unusual light, and artists and writers find inspiration in the altered world around them. Lord Byron's gloomy verses and Turner's fiery paintings are as much products of volcanic particles as they are of human imagination. In this way, volcanic winters are not just stories of disaster, but also of culture and creativity born from strangeness. There is perhaps a lesson in this. The atmosphere that shelters us is delicate, vulnerable to both natural and human forces. Volcanoes, with their sudden injections of ash and sulfur, show how quickly it can change. Human activity, with its steady accumulation of greenhouse gases, shows how persistently it can shift. Both reveal that our climate is not guaranteed. It is balanced, dynamic, and deeply tied to the life that depends upon it. When we think of volcanic winters, we're reminded not only of the violence of eruptions, but of the fragility of sunlight itself. A few degrees colder and harvests collapse. A slightly dimmer sky and society's struggle. Yet, within that fragility is resilience too. People adapt, migrate, tell stories, and even paint sunsets that glow brighter for their fleeting strangeness. In the end, volcanic winters show us that Earth's climate is not a backdrop, but an active player in the drama of history, capable of shaping the path of civilizations with a flicker of an eruption thousands of miles away. When a volcano unleashes its fury, the first impression is often one of finality. Landscapes are buried beneath ash. Forests are flattened by hot flows of gas and rock, and rivers vanish under fields of lava. Life seems to vanish in an instant, as though the clock of nature has been reset to zero. Yet the story does not end there. In the stillness after the eruption, when the smoke clears and the ground is coated in a gray blanket, life begins its slow return. What seems like desolation is actually the opening act of renewal. Time and again, history shows that ecosystems recover, often in surprising ways, guided by resilience and an unyielding drive to endure. The first arrivals in these shattered worlds are often the most unassuming. Pioneer species, lichens, mosses, and hardy bacteria, creep in where nothing else dares. Lichen, those strange partnerships between fungi and algae, are particularly adept at colonizing bare rock. They cling to the cooled lava, their tiny filaments reaching into cracks, breaking stone grain by grain as they extract nutrients. With each season, they create the faintest traces of soil. Mosses follow, holding moisture and further softening the barren landscape. To a casual glance, these might look like little more than stains of green on a wasteland. But in truth, they are the vanguard of an army that will eventually transform lifeless rock into thriving ecosystems. Once the soil begins to form, other plants can move in. Grasses, with their deep roots and ability to spread quickly, take hold in the fine ash. Seeds carried by wind or birds find their place in the new ground. Over decades, shrubs and small trees return, their roots binding the soil and creating shade for other species to flourish. Animals follow, first insects and small birds, then mammals. What was once devastation becomes a mosaic of life, often more diverse and fertile than before the eruption. In Iceland, fields of dark lava from eruption centuries ago are now covered in thick carpets of moss, glowing green under the low northern sun. In the Pacific Northwest, Mount St. Helens, which erupted in 1980, has since become a living laboratory where scientists observe how quickly forests return. Elk graze in meadows that were once sterile, and lakes formed by the eruption now brim with fish. The process is not uniform. Some places recover more quickly than others, depending on rainfall, soil chemistry, and climate. In the tropics, where warmth and moisture accelerate growth, forests may reclaim volcanic scars within a few generations. In colder, drier environments, the process can stretch across centuries. Yet no matter the pace, the principle remains the same. Life is astonishingly persistent, creeping back into every crack and corner, reshaping ruin into renewal. Humans, too, are part of this cycle of recovery. Communities living near volcanoes have always had to adapt, balancing risk with reward. The same eruptions that destroy villages also enrich the soil, leaving behind land that is extraordinarily fertile. That is why so many populations have returned to volcanic regions time and again. The slopes of Mount Vesuvius, despite its fiery history, have been farmed for millennia, producing grapes and tomatoes renowned for their richness. Around Java and Bali, some of the most densely populated areas on Earth, are built upon volcanic soils, where rice paddies glow emerald green. It is a testament to human resilience and pragmatism. We know the land can betray us, but the harvests it offers are too valuable to abandon. Sometimes survival requires more than return. It demands movement. When eruptions have been catastrophic enough to alter climate, people have migrated, seeking out new lands. After Tambora's eruption in 1815 and the subsequent year, without a summer, families in Europe and North America moved westward, searching for fields less battered by frost and famine. These migrations, born of hardship, reshaped nations and cultures, weaving volcanic threads into the fabric of history. The adaptability of humans is mirrored in our imagination. Volcanic landscapes have inspired myths and legends across the world, from fiery underworlds to gods aflame. These stories are not only expressions of awe, but also coping mechanisms, ways to explain, endure, and make sense of living under the shadow of such power. In a way, they reflect the same resilience found in mosses and lichens, an instinct to take what is overwhelming and turn it into something that helps life carry on. One of the most striking truths about volcanic recovery is that destruction and creation are two sides of the same process. An eruption may obliterate a forest, but the lava that cools in its place creates new land. Ash may suffocate crops, yet within a few years that same ash enriches the soil. Ecosystems are not static. They thrive on disturbance, renewing themselves through cycles of upheaval and regrowth. It is a reminder that life does not resist change. It uses it. This resilience is not just ecological, but symbolic. To stand at the edge of a cooled lava flow and see the first sprigs of green pushing through is to witness a profound truth, that life does not wait for perfect conditions. It advances wherever it can, no matter how hostile the environment. The same persistence can be seen in humans who rebuild homes on volcanic slopes, plant crops in new soils, or carry stories of eruptions into the next generation. There is something deeply comforting in this pattern. No matter how devastating an eruption may be, it is never the final word. The earth, renews itself, slowly but surely. What looks like ruin becomes the foundation for something new. The forests around Mount St. Helens now echo with birdsong again. The farmlands of Java, enriched by centuries of ash, feed millions. Even the vast calderas of Yellowstone and Taupo, carved by unimaginable violence, are today filled with forests, lakes, and life. This cycle invites reflection. For all our fears of catastrophe, life has proven time and again that it bends, adapts, and continues. From the tiniest lichen to the migrations of entire peoples, survival is a testament to flexibility and persistence. Volcanoes may remind us of our vulnerability, but they also remind us of our strength. We are not separate from these cycles. We're part of them, participants in the endless rhythm of destruction and renewal. In the end, the lesson of volcanic recovery is simple yet profound. Life finds a way. It may creep in slowly, moss by moss, or return with vigor as communities rebuild, but it always returns. In the shadows of eruptions, in the silence after the ash falls, the seeds of renewal are already present. What begins as devastation becomes, in time, a celebration of resilience, a quiet declaration that life cannot be silenced for long. Supervolcanoes are not like the cone-shaped mountains we see looming on the horizon. They often do not look like volcanoes at all, hiding beneath lakes, forests, and plains. To understand them, scientists cannot simply wait around for an eruption and take notes. It would be a very long wait and not a safe one. Instead, they rely on a blend of clever tools, careful observations, and a bit of detective work to peer beneath the surface and reconstruct the history of these immense systems. The study of supervolcanoes is a story of ingenuity, patience, and the acceptance that Earth rarely reveals all of her secrets. One of the most important tools is seismology, the study of earthquakes. Every time the ground shakes, even by the tiniest fraction of an inch, it sends waves rippling through the crust. By placing earthquake detectors around a volcanic region, scientists can listen to those waves and use them like ultrasound, mapping the structures hidden beneath. When an earthquake travels through solid rock, it moves faster, When it encounters melted or partially melted material, it slows down. By comparing the speeds and directions of these seismic waves, researchers can build images of underground rooms deep below. It is a bit like taking an X-ray of the Earth, except the patient never sits still, and the machine is always humming. Another crucial method involves GPS. Those same satellites that help you navigate on a road trip also help rock scientists track how the ground itself moves. By setting up networks of GPS receivers around calderas like Yellowstone, scientists can measure shifts of just a few millimeters. Over months or years, these tiny movements add up to patterns that reveal whether the ground is rising, sinking, or stretching. In volcanic regions, swelling ground can indicate magma pushing upward, while sinking might mean a chamber is deflating. Yellowstone, for example, has been observed to rise and fall by several inches over decades, a kind of breathing motion that tells us the system is alive but not necessarily dangerous. Satellites add another dimension to the story. Using radar, scientists can scan the Earth from space and detect subtle changes in surface elevation. This technique, known as InSAR, allows researchers to create maps of deformation across entire landscapes. If a bulge appears where none was before, it may suggest magma is gathering underground. Combined with thermal imaging, satellites can even detect areas of unusual heat, giving clues about where hot water activity is concentrated. And from hundreds of miles above, satellites provide a quiet watch over these restless giants, recording their movements day and night. But not all clues lie in the present. To truly understand supervolcanoes, researchers must also look back in time. Rocks scattered across the landscape often tell the story of past eruptions. Layers of ash, lightweight rock, and tuff reveal how powerful an event was, how far the material spread, and what kind of magma was involved. Rock scientists study the size of crystals in volcanic rocks, the composition of trapped gases, and the magnetic signatures frozen in minerals. Each piece is a data point, and when assembled, they form a narrative of eruptions long gone. Beyond rocks, scientists also look to natural archives like ice cores and lake sediments. In Greenland and Antarctica, layers of ice accumulate year after year, trapping dust, ash, and chemical signatures from volcanic eruptions around the world. By drilling deep into the ice and analyzing these layers, scientists can identify past eruptions, even those that left no evidence near their source. Sulfur spikes in an ice core, for instance, can reveal a major eruption and its timing with astonishing precision. Similarly, sediments at the bottom of lakes or oceans preserve ash layers that can be traced back to their origin. These records allow scientists to stitch together a global timeline of volcanic activity. Yet for all the instruments and archives, uncertainty remains an unavoidable part of volcanology. Predicting exactly when or how a supervolcano might erupt is beyond our current ability. The systems are simply too huge, too complex, and too slow-moving. Unlike weather, which changes by the hour, magma systems evolve over thousands of years. Scientists can say whether a caldera is restless, whether the ground is swelling or gases are increasing, but they cannot say with certainty that this means an eruption is imminent. In fact, most signs of unrest end without a major eruption. This uncertainty can be unsettling, but it is also a reminder of how science works. Knowledge is built step by step, with confidence in some areas and humility in others. Rock scientists are careful not to stoke alarm when none is warranted, emphasizing probabilities rather than certainties. The odds of a Yellowstone-scale eruption happening in any given century are vanishingly small, far less likely than more ordinary disasters like hurricanes, earthquakes, or floods. What scientists can do is monitor, learn, and improve their understanding so that if signs of real danger ever arise, humanity will be as prepared as possible. The process of studying supervolcanoes is also a collaborative effort. Seismologists, geochemists, climatologists, and satellite engineers all bring their expertise to the puzzle. International teams share data because ash in one country can affect crops in another, and a volcanic winter knows no borders. It is a global endeavor to understand phenomena that have global consequences. At times, the detective work even involves creativity. Some scientists experiment with computer models, feeding in data about magma viscosity, gas content, and chamber size to simulate what an eruption might look like. Others look at historical eruptions of smaller volcanoes to draw parallels, scaling up to imagine how those processes might play out on a supervolcano scale. These models are imperfect, but they offer insights into how ash might spread, how much sulfur might be released, and what the climatic effects could be. There is also beauty in the uncertainty. Supervolcanoes are reminders that the Earth is not entirely knowable, that beneath our feet are mysteries too vast to pin down. The very fact that we cannot predict them precisely speaks to the scale at which they operate. Time scales so long and forces so immense that human lifespans barely register. To study them is to practice patience, to accept that knowledge comes slowly, like the drip of water carving stone. In the end, the way we study supervolcanoes reveals as much about ourselves as it does about the Earth. We are curious creatures, determined to peer into the dark even when the answers are incomplete. We build instruments that can measure movements smaller than a human hair. We drill into ice older than civilization. And we read stories written in crystals and ash. All of this effort stems from a simple truth. We live on a restless planet, and we long to understand its rhythms. So while the calderas may sleep and the magma may stir unseen, our watch continues. Through seismology, satellites, sediments, and science's careful humility, we learn a little more each year. The giants remain mysterious, but not silent. They speak in tremors, in gases, in records frozen in ice, and in the landscapes they leave behind. Listening to them requires patience. But in that listening, we come closer to grasping the immense, slow heartbeat of the Earth itself. Long before earthquake detectors and satellites, people faced the thunder of volcanoes with nothing more than their eyes, ears, and imaginations. When the ground shook, when mountains split open, and rivers of fire poured forth, there was no scientific vocabulary to explain underground rooms or tectonic plates. Instead, communities turned to stories. Myth and legend became the framework through which they made sense of the chaos, giving shape to the unseen forces beneath their feet. To us today, these tales are windows into how cultures wrestled with the mysteries of fire, fear, and survival. In many places, eruptions were explained as the work of gods. The ancient Greeks told of Hephaestus, the divine blacksmith, hammering away in his forge beneath Mount Etna. Each tremor, each puff of smoke was said to be the sparks of his labor as he forged weapons for the gods of Olympus. To live near Etna was to live near the workshop of a deity, both a blessing and a danger. The mountain's fire was divine, beyond human control, but at least it was understood within the familiar framework of myth. In Polynesia, the story takes another form. On the Hawaiian Islands, the goddess Pele is revered as the spirit of fire and volcanoes. She is passionate, sometimes wrathful, and her presence is felt in every flow of lava across the islands. Legends tell of her battles, her loves, and her wanderings from island to island, shaping the land as she moves. Even today, offerings of flowers and food are left at her sacred sites. For Hawaiians, Pele is not just a myth of the past, but a living force, a reminder that the landscape itself is animated by spirit. Further north, in Norse mythology, volcanoes were sometimes tied to the fiery realm of Muspelheim, a land of heat and flame ruled by the fire giant Surtur. Though the Norse didn't live in volcanic regions like Indonesia or Italy, their sagas still wove fire into the grand cosmology of the world's creation and destruction. For them, eruptions were reminders of the chaos from which the world was born and to which it might someday return. In Japan, Mount Fuji has long been a sacred symbol, wrapped in both beauty and danger. Myths spoke of Fujin, the god of wind, and Raijin, the god of thunder, as forces intertwined with the mountain's eruptions. Shinto traditions viewed Fuji as the dwelling place of deities, and its eruptions were signs of their displeasure. Pilgrimages to the mountain became acts not only of reverence, but also of appeasement, a way for humans to coexist with a force far larger than themselves. Elsewhere, dragons often became the chosen symbols to explain volcanic fire. In European folklore, dragons were imagined as hoarders of treasure, lurking in caves and mountains. Their fiery breath and subterranean layers were natural metaphors for the smoking mountains. When lava spilled forth, it could be seen as a dragon stirring in its sleep, breathing out heat and fury. In Iceland, where volcanic activity is common, folk tales are filled with spirits, trolls, and serpents hidden in the hills. These beings were not distant gods, but neighbors, forces to be respected, placated, or avoided. For the peoples of Indonesia, where volcanoes dominate the landscape, myths abound. Mount Merapi, one of the most active volcanoes in the world, is said to be the dwelling place of spirits who govern both fire and fertility. Rituals are performed to honor these spirits, acknowledging the dual nature of the mountain, destructive yet life-giving. The volcanic soil provides rich harvests even as the mountain threatens to erupt without warning. Myth becomes a way of negotiating with this paradox, turning fear into ritual and chaos into tradition. What all these stories share is a recognition of power beyond human control. Volcanoes erupt without warning, indifferent to human concerns. Faced with such forces, ancient people sought comfort in explanation, even if that explanation came in the form of gods, dragons, or restless ancestors. To imagine Pele shaping the islands or Hephaestus working his forge was to place eruptions within a human story, to make the terrifying at least somewhat understandable. These myths also served a practical role. By embedding natural events into stories, communities passed down knowledge of volcanic behavior. A tale of a god's wrath might, in fact, encode memories of past eruptions, reminding future generations of the dangers of certain valleys or the signs of impending disaster. In this way, myth became both spiritual and educational, a cultural tool for survival. There is also something deeply human in the way these myths reflect our need for narrative. Volcanoes are unpredictable, and unpredictability is unsettling. By wrapping eruptions in stories, people could feel a sense of order, however fragile. A volcanic eruption was no longer a meaningless disaster, but an act of a god, a battle of giants, or the stirring of a dragon. The world remained dangerous, but at least it was not random. There was intent, there was reason, there was story. And even now, in the age of geology and volcanology, these myths retain their power. Scientists may explain eruptions with terms like rhyolitic magma or caldera collapse. But for many, the old stories continue to resonate. Tourists to Hawaii still hear of Pele. Pilgrims still climb Mount Fuji. And Icelandic folklore still whispers of hidden beings in the hills. The myths do not vanish in the face of science. They coexist, offering different ways of seeing the same fiery mountains. Volcanoes embody extremes, creation and destruction, beauty and terror, fertility and death. It is no wonder that human imagination has always reached for metaphor when confronting them. Whether in the forge of Hephaestus, the wrath of Pele, the dragons of Europe, or the spirits of Merapi, these stories capture the essence of our relationship with the land. They remind us that we are not separate from the earth, but deeply entangled with its moods and movements. There is comfort in these myths even today. When faced with chaos, we tell stories. When the ground shakes and the sky darkens, narrative is a way of holding on to meaning. Myths of fire are not just quaint relics of the past. They are testaments to human resilience, creativity, and the need to make sense of a world that can turn violent in an instant. They reveal that even in the face of overwhelming natural power, people have always found ways to weave the inexplicable into the fabric of culture, ensuring that fear could be transformed into something enduring, something shared, something that gave shape to the mystery of the Earth's fiery heart. Volcanoes often take center stage in the human imagination as destroyers, as sudden agents of chaos that bury towns in ash or darken skies with towering clouds. Yet if we pause and look closer, their story is far richer. For every eruption that devastates, there is a quieter legacy that nourishes. Volcanoes are not merely wrecking balls of nature. They're also builders, gardeners, and providers. The very ground we walk upon, the soil that feeds us, and even the heat that lights our homes in some regions are gifts that flow, in one way or another, from volcanic fire. One of the most immediate blessings of volcanoes is the fertility of their soils. When lava cools and volcanic ash settles, it may look like barren rock and lifeless dust. But over time, wind, rain, and the slow chemistry of weathering transform these materials into some of the most nutrient-rich soils on Earth. Volcanic soils, known as andesols, are packed with minerals like potassium, phosphorus, and magnesium, all essential for plant growth. Farmers throughout history have recognized this, often settling in the shadows of volcanoes despite the risks. The slopes of Mount Vesuvius, famous for its fiery temper, are also home to vineyards that produce grapes bursting with flavor. The Indonesian island of Java, where eruptions have toppled villages for centuries, is one of the most densely populated and agriculturally productive regions on the planet. Rice paddies gleam green against the backdrop of smoking peaks, a vivid illustration of how destruction can be reborn as abundance. This paradox, danger paired with fertility, is one reason volcanic landscapes have long attracted human settlement. It is not simply stubbornness that keeps people returning after each eruption. It is pragmatism. The harvests are too generous to abandon, the soils too rich to leave. What volcanoes take with one hand, they often return with the other, offering sustenance to future generations. Volcanoes also provide treasures, locked in the rocks themselves. Minerals and metals formed in volcanic environments have fueled human industry for millennia. Copper, silver, gold, and even diamonds can be linked to volcanic processes. The intense heat and pressure beneath the surface create conditions where these valuable materials crystallize and accumulate. Entire economies have been shaped by mining in volcanic regions, from the copper belts of South America to the obsidian quarries of the ancient world. Obsidian, volcanic glass, formed when lava cools rapidly, was once prized as one of humanity's sharpest tools, its edges far keener than metal blades. Long before steel, volcanic fire armed our ancestors and gave them the means to hunt, build, and defend. Another gift lies not in the solid rock, but in the heat itself. Geothermal energy, drawn from the warmth of magma deep underground, has become an important renewable resource. In Iceland, a land dotted with geysers and hot springs, geothermal power provides much of the nation's heating and electricity. Homes are warmed not by fossil fuels, but by the quiet borrowing of Earth's own heat. In places like New Zealand, Kenya, and parts of the United States, geothermal energy is tapped to generate electricity, reducing reliance on more polluting sources. It is a reminder that volcanoes are not only symbols of destruction, but also of sustainability, offering clean energy if we are willing to harness it wisely. On a grander scale, volcanoes have shaped the very continents themselves. Without eruptions, there would be no land rising above the seas. The islands of Hawaii exist solely because of volcanoes piling lava upon lava, building mountains from the ocean floor until they breach the surface. Iceland, straddling the mid-Atlantic ridge, is the product of eruptions pushing up a country from beneath the waves. Even the continents we live on today were pieced together by ancient volcanic activity. The outpouring of magma that thickened crust and stitched together land masses. The air we breathe owes its existence in part to volcanic exhalations, water vapor, carbon dioxide, and other gases that helped form Earth's early atmosphere. Life as we know it would not exist without the fiery contributions of volcanoes. It is tempting to see eruptions only in terms of their immediate destruction. But zooming out to a geological timescale reveals their creative side. Every mountain, every fertile valley, every new island tells the story of fire transformed into foundation. Even the ocean floors are continuously renewed by volcanic processes at mid-ocean ridges, where melted rock wells up and spreads outward, creating fresh crust. We are, in a sense, walking on the cooled remains of billions of eruptions stretching back through deep time. There is a poetic symmetry in the dual role of volcanoes. They are both destroyers and creators, erasers and authors. When Mount St. Helens erupted in 1980, it flattened forests and scoured rivers. Yet within years, new plants sprouted in the ash, and elk returned to graze. When Krakatoa erupted in 1883, it obliterated much of the island. But from its shattered remnants grew new land, Anak Krakatau, the child of Krakatoa, which continues to rise from the sea. Out of endings come beginnings, written in lava and ash. Even human culture has been enriched by volcanoes in subtle ways. From the myths of fire gods and dragons to the inspiration for art and literature, volcanic power has sparked imagination as much as fear. Cities, economies, and traditions have grown in volcanic regions, their rhythms tied to the cycles of eruption and renewal. The black sands of beaches, the pumice stones used in daily life, the obsidian blades of ancient craftsmen. All are quiet reminders of the gifts hidden within volcanic destruction. It is worth reflecting on the balance volcanoes embody. They remind us that creation and destruction are not opposites, but partners. The soil that grows food owes its richness to past eruptions. The continents we inhabit were built by volcanic fire. The clean energy of the future may well flow from the same geothermal heat that once terrified villages with sudden blasts. Even the catastrophes of volcanic winters, dimming skies and cooling summers have nudged human history in unexpected directions, shaping migrations, harvests, and cultures. To see a volcano as purely a threat is to miss half the story. To see it only as a benefactor is to overlook its risks. The truth lies in the pairing. Volcanoes give by the same processes through which they take away. They destroy villages, then create fertile fields. They collapse mountains, then build new islands. They bury forests, then nurture new ecosystems. In their fire lies both danger and generosity. Perhaps this is why volcanoes hold such fascination. They embody the cycles of life itself: birth, death, and renewal, compressed into landscapes of ash and stone. They are reminders that nothing is permanent, that even devastation contains the seeds of creation. To live in their shadow is to live with both risk and reward, but also to live in the presence of Earth's most dramatic expression of its own vitality. So when we look upon a volcanic field, a black sand beach, or a fertile vineyard thriving on volcanic soil, it is worth remembering the paradox that makes it possible. The very forces that can take away so much also give abundantly. Volcanoes are not simply the monsters of geology. They're also the gardeners of the planet, the builders of continents, and the keepers of the deep fire that makes Earth not just a rock in space, but a living, evolving world. Across the world, the names of Yellowstone, Taupo, and Toba carry a certain quiet weight. They are the sleeping titans of our planet, the supervolcanoes whose past eruptions reshaped landscapes and, in some cases, touched the trajectory of life itself. To hear their names can stir unease, as if they are looming disasters waiting to happen. Yet the story of these giants today is one of science, vigilance, and above all, perspective. They are watched more closely than almost any other natural systems on Earth. And what we know about them offers not just caution, but also comfort. Yellowstone, perhaps the most famous of the three, has been the subject of both serious study and sensational headlines. Some call it a ticking time bomb. Others claim it is overdue for an eruption. The truth, however, is more nuanced. Scientists at the Yellowstone Volcano Observatory maintain a dense network of earthquake detectors, GPS stations, and gas monitors across the park. These instruments track the tiniest tremors, the subtlest rises and falls of the ground, and the faintest whispers of carbon dioxide and sulfur gases escaping from below. Even satellites peer down from orbit, measuring surface deformation with precision finer than a dime. What these tools show is a dynamic system, one that breathes, swells, and subsides, but not one that shows signs of imminent catastrophe. The geysers and hot springs that delight visitors are expressions of heat moving upward, not warnings of eruption. The probability of Yellowstone producing another super eruption in the next several thousand years is extraordinarily low, far smaller than the chances of facing hazards like earthquakes, hurricanes, or even meteor impacts. Half a world away in New Zealand, Lake Taupo rests quietly in its basin, ringed by forests and towns, its waters shimmering in the sun. Yet Taupo, too, has a violent past. Its eruption around 1,800 years ago ranks among the most powerful in the last few millennia. Because of that history, it is monitored closely by GNS Science, New Zealand's Geological Research Institute. Earthquake stations encircle the lake, gas emissions are studied, and scientists even examine the chemistry of the lake water itself for signs of change. Taupo does experience occasional earthquakes and small hydrothermal bursts as magma shifts deep below. But none of these point toward a super eruption. They are simply the natural flexing of a living system, unsettling to read about in headlines, but not unusual in the life of a caldera. The odds of another Taupo-sized eruption in the foreseeable future are vanishingly slim. What is far more likely are small, localized events, minor eruptions that might affect the surrounding region, but would not shake the wider world. Then there is Toba in Indonesia, the colossus whose eruption 74,000 years ago may have dimmed the skies of the entire planet. Today, Lake Toba stretches across more than 60 miles, its blue waters belying the magnitude of the scar it fills. Indonesian scientists, working with international partners, monitor Toba carefully. Instruments measure the deformation of the lake floor, track gases, and listen for earthquakes that might suggest magma is on the move. As with Yellowstone and Taupo, what emerges is a portrait of a system that is alive but calm. Toba shows no indication of gearing up for another eruption on the scale of its ancient outburst. If it does erupt again, and all volcanoes eventually do, it will almost certainly be in smaller, less catastrophic ways. The challenge of discussing supervolcanoes lies in scale and time. Human lifespans are brief, measured in decades. Even civilizations themselves rise and fall in just a few thousand years. Super eruptions, on the other hand, occur over spans of hundreds of thousands or even millions of years. From our perspective, the gaps between them look enormous. From the Earth's perspective, they are part of a slow rhythm, like a heartbeat too deep for us to hear. To say that Yellowstone last erupted 640,000 years ago and Taupo 26,000 years ago might sound like ticking clocks, but those numbers are averages, not schedules. Volcanoes do not operate on timetables, and the very idea of one being overdue is a myth. What we can say with confidence is that the chance of a super eruption happening in our lifetimes or in the next several dozen generations is incredibly small. Studies suggest the probability is less than 1 in many tens of thousands for any given year. By comparison, the likelihood of experiencing more familiar hazards, storms, floods, or regional volcanic eruptions, is many times greater. If one wishes to lose sleep over natural risks, there are far likelier candidates than the slumbering calderas of Yellowstone, Taupo, or Toba. This does not mean scientists are complacent. Quite the opposite. These regions are among the most intensively studied on the planet precisely because of their potential. The data gathered not only helps us keep watch for any unusual changes, but also deepens our understanding of volcanic systems in general. What we learn from Yellowstone can be applied to smaller volcanoes around the world, improving forecasts and potentially saving lives in places where eruptions are far more likely. In this sense, supervolcanoes act as vast natural laboratory, their very scale offering opportunities for discovery. For people living near these giants, the greatest dangers are not world-ending blasts, but smaller, more localized events. At Yellowstone, hydrothermal explosions can occur when steam builds beneath the surface, creating craters a few hundred meters wide. These are dangerous but confined, unlikely to affect more than the immediate area. Around Taupo, minor eruptions or earthquakes are more probable than another Orowanui-scale event. In Indonesia, smaller volcanic systems pose far greater risks to communities than Toba does today. In each case, the everyday reality is less dramatic than the myths that surround these places. It is worth reflecting, too, on why stories of supervolcanoes capture so much attention. There is a fascination with events that dwarf human experience, with forces so immense that they remind us of our smallness. The idea of a single eruption, cooling the globe, or altering civilizations, taps into both awe and fear. Yet awe need not be anxiety. If anything, the long slumber of these giants should be reassuring. They show us that the Earth's most dramatic powers move on scales far slower than our own, offering us a stability we rarely acknowledge. And so, while it is true that Yellowstone, Taupo, and Toba are alive, it is also true that they are extraordinarily unlikely to erupt catastrophically in our lifetimes. Their stories are not ones of looming doom, but of patience and perspective. They are reminders that the earth is vast and powerful, yet also generous with time for us. They offer not only lessons in geology, but also a kind of quiet comfort. The giants sleep, and they will almost certainly continue to do so long after we are gone. The danger of today, then, is not the eruption itself, but the misunderstanding of it. It is easy to sensationalize, to frame Yellowstone as a threat poised to erupt at any moment. But the science tells a calmer story, one of careful monitoring, vanishingly small probabilities, and the reassurance that while supervolcanoes are a real part of Earth's history, they are not the storms of our present. To live in their shadow is not to live in constant peril, but to live in a world that is alive, dynamic, and in its vast patience, far more forgiving than we often give it credit for. Human beings like to imagine that we're in charge. We grow food on every continent, move goods across oceans, and connect the world with invisible signals that leap between satellites and towers. Yet for all our ingenuity, there is a quiet truth. Our systems are fragile. They depend on stability in ways that volcanoes do not. A single massive eruption, even one far away, has the potential to ripple through the networks we rely upon. While the Earth can shrug off an eruption as part of its natural rhythm, our societies, with their delicate chains of supply and communication, are far more vulnerable. Perhaps the most fundamental weakness lies in food. Modern agriculture feeds billions, but it is a finely balanced enterprise. Crops are planted in spring, harvested in summer or autumn, and shipped across borders to meet global demand. Disrupt that rhythm, and shortages appear quickly. A super eruption would not destroy fields directly in every corner of the world, but the ash and gases it lofts into the sky could cool the planet and shorten growing seasons. Even a temperature drop of 1 or 2 degrees Celsius can mean harvest failures across multiple regions. Wheat and rice, staples for much of humanity, are particularly sensitive to unusual cold and irregular rainfall. The interconnectedness of our food supply makes the problem worse. In earlier times, a poor harvest in one valley was a tragedy for that valley, but it did not necessarily ripple outward. Today, nations import and export enormous quantities of grain, fruit, and vegetables. A disruption in one country can cascade through the system, raising prices and reducing access everywhere. When Mount Tambora erupted in 1815, its ash dimmed the skies and caused crop failures across Europe and North America. That was in an age when global trade was rudimentary compared to now. Imagine the same scenario today, when food is shipped by air and sea in colossal volumes, and the fragility of our system becomes clear. Ash itself is a hazard, not just for crops, but for the movement of goods and people. Volcanic ash is not like the soft flakes of a fireplace. It is pulverized rock, sharp and abrasive. When it falls thickly on farmland, it can suffocate plants, clog irrigation systems, and contaminate water supplies. A blanket of ash, just a few centimeters thick, can render fields useless for an entire season. But perhaps more disruptive in our globalized age is the effect on air travel. Jet engines do not respond kindly to volcanic ash. Ingested into turbines, the particles melt and then resolidify on the blades, choking engines and risking catastrophic failure. In 2010, the eruption of Eyjafjallajökull in Iceland illustrated this vulnerability vividly. Although modest compared to the giants of history, it sent a plume of ash into European airspace, grounding flights for days. Millions of passengers were stranded, and airlines lost billions in revenue. That was the result of a relatively small eruption. Scale that up to the ash clouds of a supervolcano, which could spread across entire hemispheres, and international aviation would grind to a halt. Passenger planes, cargo flights, and even military operations would be grounded. The skies would fall quiet, and with them, the swift movement of people and goods that modern economies rely upon. On the ground, ash also wreaks havoc with infrastructure. It can collapse roofs under its weight when wet, clog machinery and short-circuit power systems. Power grids are particularly vulnerable. Ash that settles on high-voltage lines and substations can become conductive when damp, leading to widespread outages. In an age when electricity underpins everything from hospitals to water treatment, such failures would multiply the disruption. Communications, too, are at risk. Satellite dishes and antennas coated in ash lose effectiveness, while cables and data centers depend on uninterrupted power. Even undersea cables, though physically safe, would be useless without functioning grids on land to feed the signals. It is easy to underestimate just how interwoven modern systems have become. Consider the smartphone in your hand. It may contain rare earth minerals mined in Asia, chips manufactured in North America, and assembly completed in another part of the world entirely. Each step relies on transport, energy, and communication. A massive eruption that grounds planes, disrupts ports, and cuts power would ripple into every corner of the supply chain. Suddenly, the most ordinary objects, whether a loaf of bread or a battery, become difficult to obtain. Beyond material goods, there is the question of health. Ash clouds irritate lungs, contaminate drinking water, and create long-term hazards for communities. Hospitals, already strained by power cuts and supply shortages, would struggle to cope. Respiratory illnesses would spike, especially among the vulnerable. Volcanic gases like sulfur dioxide, when mixed with water in the atmosphere, form acid rain, further damaging crops, buildings, and human health. The disaster would not be one dramatic moment, but a prolonged challenge, testing, resilience over months and years. Yet even in this vulnerability, there is resilience. Human beings are remarkably adaptable, and societies have learned from past eruptions. Modern monitoring means we would not be caught unaware. Scientists can detect signs of unrest well in advance, allowing for some preparation. Governments have contingency plans for food storage, emergency power, and communication backups. After Eyjafjallajökull, for example, aviation authorities revised guidelines for flying through low concentrations of ash, reducing the likelihood of such widespread disruption from a smaller eruption. Still, the reality remains: our global civilization is more interconnected than any before it, and that interconnection is both strength and weakness. It allows us to share resources and knowledge across continents. But it also means that a shock in one place is felt everywhere. A supervolcano would be such a shock, not because it would wipe out humanity in one fiery moment, but because it would press on the delicate systems that sustain billions of lives. Reflecting on this vulnerability is not meant to instill fear, but perspective. Volcanoes remind us that we're part of a living planet, and that our inventions, though extraordinary, do not free us from nature's rhythms. They show that resilience must be built not just into buildings and machines, but into systems of cooperation and community. For while ash can ground planes and disrupt grids, it cannot extinguish the human capacity to adapt. Communities would ration, migrate, innovate, and survive, just as our ancestors did after Tambora and Krakatoa. So, while the dangers are real, they're not insurmountable. They highlight the fragility of our dependence on complex networks, but they also reveal the strength that comes from knowledge, foresight, and the shared determination to endure. A volcanic eruption, no matter how vast, would be a reminder that the world is not a machine we control, but a living planet we share. A planet that gives and takes, that disrupts and renews, and challenges us to remain humble, flexible, and resilient. The Earth has always had its moments of fury, and humanity, small and fragile upon its surface, has always been forced to reckon with them. While we cannot stop a volcano from erupting, we can look backward and learn from the footprints left in ash and stone. Tambora, Toba, Taupo, Krakatoa. Each of these events has left scars not only on the land, but also in human memory. In their stories lie lessons of resilience, failure, and adaptation. Quiet wisdom passed down from those who lived through times when the sky itself turned hostile. Take Tambora in 1815, perhaps the clearest lesson etched into recorded history. The eruption itself destroyed villages in Indonesia, but it was the ripple effects that showed just how far a mountain's reach could extend. Sulfur and ash injected into the upper atmosphere dimmed the sun, plunging the world into the infamous year without a summer. Crops failed in North America and Europe. Prices of food soared, and hunger gnawed at communities that never even heard of Sumbawa. Some regions coped by sharing what little they had or migrating to more fertile lands. Others descended into desperation and unrest. The famine in Switzerland inspired riots. In Germany, starving families abandoned homes to search for food. And in Ireland, already poor, the effects were devastating. From Tambora, we learned that disasters need not happen on our doorstep to affect us, and that global connections, though far less intricate than the now, make us all vulnerable to distant events. Much further back in time, the eruption of Toba, around 74,000 years ago, paints an even starker picture. While debates continue about the exact extent of its impact, there is evidence of dramatic cooling, perhaps enough to stress ecosystems across continents. Some scientists once argued that it reduced the human population to a tiny remnant, creating a genetic bottleneck. Whether that extreme view is correct or not, it is clear that early humans lived through a period of sudden hardship. Archaeological sites in Africa and India show continuity, suggesting that while the eruption altered lives, people adapted in place, finding new foods, shifting their movements, and learning to endure in a dimmer world. The lesson from Toba is not of extinction, but of persistence. Even in the harshest conditions, humans found ways to survive. Taupo's eruption around 26,000 years ago and its later Hatepe eruption about 1,800 years ago teach another kind of lesson. The immense blast of the earlier eruption reshaped New Zealand's North Island, leaving a lake where a mountain once stood. Later, the Hatepe eruption was one of the largest in the past 2 millennia, ejecting ash that reached as far as China. For the Maori who settled the region centuries later, oral traditions preserved stories of the land's fiery past. These myths served as cultural memory, reminding communities of the power and spirit of the land they inhabited. Embedded within the legends is a subtle guidance: respect the forces beneath the surface. The wisdom here is cultural as much as geological. Stories can carry survival knowledge across generations. Krakatoa's eruption in 1883 provides yet another chapter in the Earth's long record. The explosion shattered an island, produced tsunamis that killed tens of thousands, and sent shockwaves around the world. People in London heard the sound, and barometers across the globe recorded its pulse. Yet even amid devastation, communities rebuilt. New land rose from the sea, and within a generation, Anak Krakatau, the child of Krakatoa, emerged from the waves. From this story, we learn that destruction is often followed by renewal, and that nature has a way of filling voids left behind. What unites these examples is not simply the violence of eruptions, but the human responses to them. Some societies bent and did not break. Others cracked under the strain. Where there was cooperation, sharing, and flexibility, survival was possible. Where fear, inequality, or rigidity ruled, disaster deepened. In the case of Tambora, hunger drove unrest in Europe, but it also drove innovation. In the gloomy summer of 1816, Mary Shelley, confined indoors by the cold and rain, wrote Frankenstein. And Lord Byron penned Darkness. Even in hardship, human creativity found expression, turning disaster into art. Looking at these past eruptions also helps us temper our expectations for the future. Not every massive eruption will end civilizations, and not every ash cloud will plunge the world into famine. The impacts vary with geography, timing, and the preparedness of societies. What remains consistent, however, is that disruption follows, and adaptation is required. History suggests that our greatest vulnerability is not in the eruption itself, but in how we respond afterward. The quiet wisdom we inherit from the past is therefore twofold. First, we must respect the scale of natural forces, acknowledging that they can disrupt even the most secure-seeming societies. Second, we must recognize the resilience embedded in humanity. People have endured dim skies, ruined harvests, and shifting landscapes, and though they often suffered, they also learned, migrated, and found ways to carry on. The myths and stories born from eruptions serve as reminders of this dual lesson. Pele in Hawaii, Hephaestus beneath Etna, the spirits of Merapi in Indonesia. These tales are more than folklore. They are cultural memory, ways of keeping alive the knowledge that mountains can move, skies can darken, and the land can shift beneath our feet. Science now offers more precise explanations, but the stories still matter. They root us in the understanding that we're never entirely safe from the deep fires of the earth, and that we must remain humble in the face of forces beyond our control. Perhaps the greatest lesson of all is patience. Supervolcanoes, after all, operate on time scales far beyond human reckoning. Toba, Yellowstone, Taupo. These giants erupt once in many tens or hundreds of thousands of years. They do not follow schedules or pay attention to our calendars. To live in their shadow is to live with a paradox. The danger is real, but the time scales are vast. The Earth teaches us through these eruptions that change is inevitable, but also that endurance is possible. So when we look back at Tambora's starving fields, Toba's dim skies, or Krakatoa's shattered island, we are not just reading about disasters. We are reading about survival. We're reading about the human capacity to adapt, to learn, and to create meaning from catastrophe. History does not give us certainty about the future, but it does give us guidance that cooperation, memory, and humility are the best tools we have when the ground beneath us reminds us of its restless heart. The past, then, is more than ashes and scars. It is a teacher offering quiet wisdom to those willing to listen. Volcanoes show us destruction, yes, but also resilience. They tell us that survival is not about avoiding every disaster, but about living with them, adapting to them, and carrying their lessons forward. And in that, perhaps, lies the greatest gift of all, the knowledge that even in the face of Earth's greatest upheavals, life, fragile, inventive, and stubborn, finds a way to endure. When people hear the word supervolcano, their minds often leap straight to Yellowstone, or perhaps to Toba with its icy shadow on human history. Yet Yellowstone and Toba are not the only titans of Earth's past and present. There are other giants, quieter in reputation, but no less impressive in scale. Some erupted long before humans ever walked the planet, their stories written only in rocks and landscapes. Others still slumber beneath cities and coastlines, their power overshadowed by more famous names. These are the supervolcanoes we don't often talk about, the hidden colossi whose legacies remind us that the Earth remembers more than we do. Take La Garita in what is now Colorado. Around 28 million years ago, this region of North America was the stage for one of the largest known eruptions in Earth's history. The eruption produced the Fish Canyon Tuff, a deposit so vast that rock scientists still marvel at its scale. Estimates suggest that more than 5,000 cubic kilometers of material were expelled, several times larger than Yellowstone's biggest eruptions. To put that in perspective, if Tambora's eruption in 1815 was a thunderclap, La Garita was a symphony of explosions that rewrote entire landscapes. Mountains were leveled, valleys buried, and the atmosphere filled with ash that would have circled the globe. Yet La Garita is a name few outside geology circles recognize. Unlike Yellowstone, it is not marked by geysers or hot springs. Unlike Toba, it did not brush against the story of humanity. Its eruption is buried in deep time, when mammals were still diversifying after the extinction of the dinosaurs. There were no humans to witness it, no legends to carry its memory forward. Instead, its story survives only in the cliffs and mesas of Colorado, where layers of volcanic rock stretch across the land like the pages of a forgotten book. La Garita reminds us that Earth's most profound events are not always those that touch human history, but those that shape the very stage upon which that history later unfolded. Across the Atlantic lies another giant, one far closer to modern lives, the Campi Flegrei, or Phlegraean Fields, near Naples in Italy. Unlike La Garita, Campi Flegrei is not lost in ancient epochs. It is very much alive, a sprawling caldera beneath the bustling population of southern Italy. Its last major eruption occurred around 39,000 years ago, producing the Campanian ignimbrite, a blanket of ashen rock that covered much of Europe. That eruption is thought to have been powerful enough to affect climates and perhaps even influence the survival of early human groups across the continent. The area still steams and shifts today, its ground rising and falling as magma stirs below. Yet despite its immense size and potential, Campi Flegrei is often overshadowed by its more glamorous neighbor, Mount Vesuvius. Vesuvius looms as a classic volcanic cone, famous for burying Pompeii in the year 79. It is dramatic, visible, and photogenic. Campi Flegrei, by contrast, is subtle. Its vast caldera hidden beneath cities, fields, and the Bay of Naples. Visitors walk through streets, past cafes and cathedrals, not realizing that beneath them lies one of the most dangerous volcanic systems on Earth. It does not announce itself with a cone. It hides in plain sight, a reminder that the most powerful forces are sometimes the least obvious. These overshadowed giants challenge the way we think about history. Yellowstone captures headlines, but it has not erupted in over 600,000 years. La Garrida's colossal outburst is so far in the past that it exists only in rock strata. Campi Flegrei simmers beneath millions of people, but its name rarely appears outside scientific reports. The Earth has many such scars and slumbering giants, calderas across South America, Asia, and beyond that tell us super eruptions are not unique to a few well-known places. They are part of the planet's deep rhythm, scattered across continents and ages. What is striking is how little human memory stretches compared to the Earth's. A few thousand years and oral traditions fade. A few tens of thousands and even archaeology struggles to keep track. But the Earth remembers in stone. La Garrita's tufts, Campi Flegrei's deposits, Taupo's pumice, geological diaries recording events that no human eye saw. They remind us that our stories are only one thread in a much older tapestry, and that much of what the Earth has done lies beyond the span of human history. At the same time, these forgotten or overlooked supervolcanoes offer lessons for today. La Garrida shows the upper limits of what Earth can unleash, a benchmark for the scale of eruption possible on this restless planet. Campi Flegrei demonstrates that supervolcanoes are not confined to remote wilderness. They can exist beneath thriving cities, shaping the lives of millions. In both cases, awareness is the first step toward wisdom. We may not need to fear these giants daily, but knowing their presence reminds us of our place in the larger story of the Earth. There is also a kind of quiet humility in acknowledging the eruptions we don't talk about. They whisper of the countless events that shaped our world long before we arrived. The upheavals that laid down soils, built mountains, and altered climates. They are a reminder that history is not just what humans record in books, but what the Earth writes in rock and ash. Our species has seen only a tiny fraction of the planet's volcanic drama, and what we think of as rare disasters are, in geological terms, recurring chapters in a long-running narrative. So while Yellowstone and Toba may dominate conversations about supervolcanoes, it is worth remembering the others. The La Garritas that roared before humanity existed. The Campi Flegrei that simmer quietly underfoot. The many calderas scattered across the continents. They are part of a larger truth, that the Earth has seen eruptions beyond our imagination and will see them again long after our brief span has passed. The Earth remembers in ways we cannot. It holds the echoes of La Garrita's fire, the breath of Campi's ash, the scars of countless giants whose names we may never know. And while we may forget, distracted by the immediacy of our own histories, the land carries those memories patiently, waiting for us to notice, to listen, and to learn. Imagine for a moment that somewhere beneath the Earth's crust, one of the sleeping giants stirred. Perhaps it is Yellowstone, Taupo, or a caldera that barely features in headlines, hidden beneath forests or lakes. Pressure builds, magma shifts, and eventually the crust gives way. The eruption that follows is not the kind we're used to reading about in the news, a glowing mountain in Iceland or a cone puffing smoke in Italy. It is something far larger, something on the scale of Tambora or even Toba, capable of sending ash across continents and cooling the climate for years. What then? Could humanity survive the next super eruption? To answer this calmly requires setting aside sensationalist imagery of apocalyptic doom and focusing instead on science. The good news is that a super eruption, no matter how vast, would not spell the end of humanity. Our species has already lived through Toba, Tambora, and countless smaller eruptions. The bad news is that survival would not be easy. The greatest challenges would not come from lava or hot flows of gas and rock. The immediate devastation would be confined to a region, but from the global after effects, the first and most dramatic impact would be the ash and gases launched high into the upper atmosphere. Sulfur particles would spread around the world, reflecting sunlight and dimming the skies. Global temperatures could drop by several degrees, creating what scientists call a volcanic winter. Growing seasons would shorten or fail entirely. Rainfall patterns would shift, and food production would plummet. In a world where billions depend on interconnected supply chains, the fragility of agriculture would quickly be exposed. The biggest risk of a supereruption is not fiery death, but hunger on a massive scale. Modern science has modeled such scenarios. One study suggested that a Yellowstone-scale eruption could lower global temperatures by as much as 5 degrees Celsius for several years. Crops in temperate regions would be especially vulnerable, and tropical regions could see rainfall patterns disrupted. In short, the very foundation of food security would be shaken. Yet survival is not out of reach. The same interconnectedness that makes us vulnerable also provides tools for resilience. Global cooperation, sharing food stores, redirecting trade, developing emergency crops, could bridge the gap. The difference between catastrophe and survival would hinge not on geology, but on governance and compassion. Technology also offers tools that our ancestors lacked. Greenhouses, hydroponics, and vertical farms can produce food even when the skies darken. Stored grains, if managed wisely, could sustain populations through lean years. Alternative food sources, algae, fungi, or even lab-grown proteins, might step in when traditional agriculture falters. None of these are perfect solutions, but together they sketch a picture of possibility. Humanity today is not the same as humanity 74,000 years ago, huddling in small groups across Africa. We are global, resourceful, and capable of planning on scales our ancestors could not have imagined. Another challenge would be infrastructure. Ash clouds could ground plains for months, power grids could fail, and water supplies could be contaminated. In affected regions, roofs would collapse under the weight of ash, and machinery would grind to a halt as particles clogged engines. Here, too, preparation matters. Buildings can be designed to withstand ash loads. Water systems can be protected. Power grids can be reinforced. The lessons from smaller eruptions, such as Eyjafjallajökull in 2010, which grounded flights across Europe, provide real-world rehearsal for what might come. Perhaps the greatest challenge, however, would be psychological. Humanity is adaptable, but fear spreads quickly. A sky that turns gray for months, sunsets that glow blood red, frosts in July, these would feel like omens. Maintaining social stability in the face of prolonged scarcity and uncertainty would be as important as distributing food or repairing infrastructure. History shows both sides of this equation, famine leading to unrest, but also hardship forging cooperation. The question is not whether humans could survive, but how we would choose to survive, together or divided. Some have even proposed technological interventions inspired by the very process of volcanic cooling itself. If eruptions can cool the planet by injecting particles into the upper atmosphere, perhaps humanity could deliberately counterbalance the effects or at least manage them. Geoengineering on this scale remains speculative, but the idea reflects a broader truth. We are no longer passive witnesses. Unlike our ancestors, we have the capacity to measure, to model, and potentially to mitigate. It is important, too, to frame probabilities correctly. The chance of a supereruption happening in any given century is extraordinarily low. Scientists estimate the odds are far less than 1%. perhaps closer to one in several tens of thousands per year. By comparison, humanity faces far greater immediate risks from climate change, pandemics, and resource depletion. Still, low probability is not zero, and given the stakes, it is wise to think in terms of preparation. Not panic, but prudence. So, could we survive the next super eruption? The evidence suggests yes. We would suffer, certainly. Millions might go hungry, economies would strain, and the fabric of daily life would fray. But extinction is not on the table. Humanity's adaptability, ingenuity, and cooperation would be the deciding factors. We survived Tambora's chill and rebuilt. We endured Krakatoa's tsunamis and carried on. We carry in our DNA the resilience of those who weathered Toba's long winter. Perhaps the calmest way to think about it is as a thought experiment in resilience. What does it mean to live on a planet that is both nurturing and volatile? How do we prepare not for certainties, but for possibilities? To ponder a future super eruption is to reflect on the balance between vulnerability and strength, fragility and resourcefulness. It is a reminder that while we cannot control the deep fires of the earth, we can control our responses, our cooperation, and our foresight. In the end, a super eruption would be a trial, but not the end of the story. The earth has endured worse, and so have we. The giants beneath the surface may stir someday, but when they do, humanity will face them not with despair, but with the quiet, stubborn resilience that has carried us through ice ages, plagues, and every upheaval before. The question is not whether we could survive, but how we would choose to shape survival into something more than endurance, into a chance to grow wiser, humbler, and more attuned to the restless planet we call home. When people think of volcanoes, they tend to picture something familiar: a conical mountain, smoke rising from its peak, lava spilling in glowing rivers down its flanks. These are the volcanoes of Earth, dramatic and dangerous, yet still bounded by the limits of our planet's geology. But step outside our world, and the picture shifts dramatically. Beyond Earth, volcanoes reach sizes and forms that make even Yellowstone seem modest. In the vastness of the solar system, volcanic activity has taken many shapes, and exploring them not only expands our imagination, but also humbles us. The giants of our world are mighty, but they are not unique. Perhaps the most famous extraterrestrial volcano is Olympus Mons on Mars. Towering nearly 22 kilometers high, it is the tallest known volcano in the solar system, nearly 3 times the height of Mount Everest. Its base sprawls over 600 kilometers, large enough to blanket an entire country. To grasp its scale, imagine a volcano so broad that if you stood at one edge, its summit would be below the horizon, hidden by the curve of the planet itself. Olympus Mons is not a supervolcano in the sense we use on Earth. It did not collapse into a caldera after a titanic blast, but its sheer size makes it a superlative of another kind. It is a shield volcano, built by countless eruptions of basaltic lava that flowed easily across the Martian surface, stacking layer upon layer for millions of years. Why is Olympus Mons so enormous compared to Earth's volcanoes? The answer lies in Mars' unique geology. First, the planet lacks plate tectonics. On Earth, the movement of plates carries volcanic hotspots away over time, creating chains of volcanoes like the Hawaiian Islands. On Mars, with no moving plates, lava poured out again and again in the same location, allowing Olympus Mons to grow taller and wider with each eruption. Second, Mars's weaker gravity allows structures to rise higher before collapsing under their own weight. Combined, these factors created a volcano so colossal that it dwarfs anything on Earth. Mars is not alone in its volcanic drama. Other planets and moons in the solar system also reveal fascinating volcanic landscapes. On Venus, for instance, the surface is littered with volcanic features. The planet is cloaked in thick clouds, but radar mapping has revealed mountains, domes, and lava plains stretching across nearly its entire surface. Some scientists believe Venus may still be volcanically active today, with heat escaping through fissures and eruptions, occasionally resurfacing parts of the planet. Its volcanoes are generally broad and flat, more like vast lava fields than towering peaks. But they testify to a world where volcanism has been one of the dominant forces shaping the landscape. Then there are the moons, where volcanic activity takes unexpected forms. Jupiter's moon Io is the most volcanically active body in the solar system. Unlike Mars or Venus, its volcanoes are not ancient remnants, but ongoing, with lava fountains erupting regularly. This activity is driven not by internal heat alone, but by tidal forces. Io is locked in a gravitational dance with Jupiter and its neighboring moons, pulled and squeezed by immense forces that generate heat in its interior. The result is a surface constantly reshaped by eruptions, glowing with lava lakes and punctuated by plumes that can rise hundreds of kilometers above the moon. If Earth's supervolcanoes remind us of our planet's restless heart, Io reminds us that volcanism can be even more extreme under different cosmic circumstances. Saturn's moon Enceladus and Jupiter's moon Europa show yet another twist: cryovolcanism, or ice volcanoes. Instead of melted rock, these worlds erupt with water, ammonia, or other volatile substances. On Enceladus, geysers shoot plumes of water vapor and ice crystals into space, creating Saturn's faint E-ring. These eruptions hint at subsurface oceans beneath the icy crust, oceans that may harbor the ingredients for life. Cryovolcanoes challenge our earthbound assumptions. Volcanism is not limited to fire and ash, but can also involve ice and water, sculpting landscapes in alien ways. Comparing Earth's volcanoes to these extraterrestrial examples highlights both our uniqueness and our shared place in the cosmos. Earth's supervolcanoes like Yellowstone or Toba are extraordinary in their power to influence climate and life, yet in sheer scale, they are modest compared to Olympus Mons. In terms of activity, they are quiet compared to Io's constant eruptions. In creativity, they are perhaps ordinary compared to the icy fountains of Enceladus. Our planet's volcanism is remarkable, but it is not the universe's only experiment in how worlds release their inner heat. These comparisons also shed light on why volcanism matters. Volcanoes, whether on Earth or elsewhere, are expressions of planetary energy, a way for worlds to cool themselves, release gases, and reshape their surfaces. On Earth, this process has been central to life itself. Volcanic gases helped form our early atmosphere. Lava built the continents and islands we live on. Super eruptions, though destructive, helped fertilize soils and influence the course of evolution. Elsewhere, volcanism may play similar roles. On Enceladus or Europa, icy eruptions may deliver nutrients to hidden oceans, creating potential havens for life. The same process that gives us both fertile fields and volcanic winters could also be nurturing alien ecosystems beneath the ice of distant moons. Looking outward also helps us reflect on perspective. When people speak of Yellowstone as terrifying or unique, it is easy to imagine it as a one-of-a-kind monster lurking beneath our feet. But in the broader context of the solar system, Yellowstone is simply one example of a much larger story. Volcanoes are a universal phenomenon, woven into the fabric of planetary evolution. They are not exceptions, but the rule, appearing wherever heat and pressure build beneath the surface. The giants of Earth are awe-inspiring, yes, but they are part of a cosmic family of fire and ice. This expanded view is comforting in its own way. It reminds us that we are not alone in experiencing the restless energy of geology. Our world is not uniquely cursed or uniquely blessed. It is one among many, shaped by forces that operate across the cosmos. To see volcanic scars on Mars, fiery fountains on Io, and icy plumes on Enceladus is to recognize that Earth's dramas are part of a shared planetary story. The Earth is not unique in its turbulence. It is unique only in that we are here to watch, to worry, and to wonder. So when thinking of supervolcanoes beyond Earth, it is worth pausing to appreciate the breadth of what volcanism means. On one planet, it can build mountains higher than anything we have ever climbed. On another, it can erupt with such violence that the surface is constantly remade. On yet another, it can hint at hidden seas where life may quietly stir. Our own supervolcanoes remind us of our vulnerability, but their extraterrestrial cousins remind us of possibility, that the processes which sustain and challenge us here may also be shaping distant worlds in ways we're only beginning to imagine. In the end, Earth's supervolcanoes are neither the largest nor the most unusual in the solar system. They are simply ours, bound into our history, our myths, and our future. Beyond Earth, the story of volcanism continues in grander and stranger forms, a reminder that the restless fire within worlds is as universal as the stars themselves. To understand supervolcanoes fully, we need to step back not just a few centuries or even a few millennia, but into the immensity of Earth's deep history. Long before cities were buried by ash or fields starved of sunlight, volcanism was at work, sculpting continents, stirring oceans, and shaping the atmosphere itself. The violent breath of the earth is not an occasional disruption to the story of life. It is one of the forces that made the story possible at all. In the earliest chapters of Earth's history, nearly 4 billion years ago, the young planet was a melted world. Its surface seethed with lava seas, pummeled by meteorites from the crowded neighborhood of the early solar system. As the crust cooled, volcanism became the great exhalation of Earth's inner heat, releasing gases that thickened the atmosphere: carbon dioxide, water vapor, sulfur, and nitrogen. These volcanic emissions created the air and seas that would eventually cradle life. Without these fiery beginnings, Earth might have been barren, a cold rock adrift in space. Even after the first oceans formed, volcanism continued to play a central role. Enormous eruptions reshaped the surface on scales beyond modern imagination. The formation of large igneous provinces, such as the Siberian Traps around 252 million years ago, poured out lava over millions of square kilometers. This outpouring coincided with the Permian extinction, the most devastating die-off in Earth's history, where more than 90% of marine species and 70% of terrestrial species vanished. The link between volcanism and extinction is stark. The gases released during such colossal eruptions altered climate, acidified oceans, and destabilized ecosystems. Volcanism has been both cradle and scythe, creating the conditions for life to flourish, and at times cutting it back with ruthless efficiency. Yet it is not only extinction that volcanism has shaped. Continents themselves owe much of their existence to volcanic processes. Subduction zones, where one tectonic plate slides beneath another, generate magma that rises to form arcs of volcanoes. Over millions of years, these arcs stitched together to create continents. The granite that underpins much of the continental crust is itself a product of ancient volcanism, crystallized from melts that cooled deep within the earth. Without this continual recycling of rock, there would be no stable landmasses for forests to grow, for animals to roam, or for humans to build civilizations upon. Supervolcanoes, in particular, have left their fingerprints across deep time. La Garita, in what is now Colorado, erupted 28 million years ago, unleashing more than 5,000 cubic kilometers of material. An eruption several times larger than anything Yellowstone has produced. Its deposits spread across much of North America, preserving a record of a cataclysm no human eye ever saw. Other massive eruptions, like those that formed the Deccan Traps in India around 66 million years ago, played a role in shaping the end of the dinosaurs. Though the asteroid impact at Chicxulub often takes center stage, the Deccan eruptions may have already stressed ecosystems, poisoning the atmosphere and warming the climate, tipping the scales against the great reptiles that had dominated for over 100 million years. These events remind us that volcanism is not just a backdrop, but a driver of change. Climate shifts, mass extinctions, and evolutionary opportunities all carry volcanic signatures. After the Siberian traps extinguished so much life, ecosystems slowly rebuilt, giving rise to new lineages. After the Deccan eruptions and the asteroid impact ended the dinosaurs' reign, mammals seized the vacant ecological spaces, setting the stage for our own eventual rise. In a paradoxical way, the greatest devastations of volcanism have also cleared the path for renewal. Fire is not only an end, but also a beginning. Even the air we breathe carries volcanic heritage. For billions of years, eruptions released carbon dioxide and water vapor into the atmosphere, fueling the greenhouse effect that kept Earth warm enough for liquid oceans. At times, too much volcanism drove the planet into overheating, creating hothouse climates. At other times, a slowdown allowed ice ages to grip the globe. The balance between volcanic input and other processes, like weathering and photosynthesis, has determined Earth's climate over deep time. Supervolcanoes, with their episodic but immense injections of gas and ash, have been punctuation marks in that longer narrative, tilting the climate suddenly before balance returned. From a cosmic perspective, volcanism is the heartbeat of a living planet. Without it, Earth would be geologically dead, like the moon, its surface frozen in time. The fact that our world still trembles, erupts, and reshapes itself is a sign of vitality, a reminder that beneath the crust lies a restless heart of melted rock. Supervolcanoes, rare though they are the grandest expressions of this vitality.